Today we're going to complete our WireShark series by learning how to find anomalies using WireShark. My name is Hank Hackerson, your trainer for today, and to get more videos like this one, make sure that you like, subscribe, and turn on the notification bell. We're going to be using the WireShark Traffic Analysis room that is inside of TryHackMe. This is a premium room, but again, as always, you can always just download WireShark onto your own computer, or you can get a free membership to TryHackMe and then use all of the free rooms that they have. They have literally hundreds of free rooms that you can leverage to get access to WireShark, and then you can use the tool in a very similar manner that I'm going to be using it today. And the only difference will be that you won't get access to the same packet capture files, the same PCAP files that I would get access to. But honestly, it's all pretty much the same. So you can find a bunch of PCAP files available through a variety of different resources for free. Just make sure that they are from legitimate resources and you don't download malware onto your computer. You can always use a antivirus tool or some kind of a scanner to just make sure that it is a legit file that you're downloading. So apart from that, the rest of it should be pretty straightforward and very similar to what I'm going to be doing today. So we have the introduction, then we have Nmap Scans, ARP poisoning, identifying hosts, tunneling traffic, Cleartext protocols for FTP and HTTP, and then we have the encrypted protocols, and then there's the bonuses, and then we have the conclusion, and then we will wrap for today. All of the timestamps for these are going to be in the description below, so if you wanted to jump around, you could definitely do that, or if you wanted to repeat a specific section, you can do that. But that's pretty much it, pretty straightforward. And it should be a really good one because it is, as you saw, there's a variety of different tasks that we have. So I think this is going to be a longer video today, and we're going to be doing some pretty advanced stuff relative to everything else we've talked about so far with WireShark. Again, this is one of those industry standard tools that you really want to get good at. So if you haven't watched the previous 2 videos on WireShark, I highly encourage you to do that because we're going to be talking about some more intermediate / advanced type stuff today. And you want to have a strong foundation before you go into this specific content that we're going to be talking about. So quick little note from Hackaholics Anonymous, and we will dive into the introduction. If you want access to my notes and exclusive downloads and to get lifetime access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers. We have the supporter, the agent, the guardian, and the master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every single month, plus so much more. And to join, you can simply click the link in the description below and you will be able to choose the tier for which you want to join. I really hope I see you in the Discord chats. If not, I hope I see you in the comment section. In the last 2 rooms, or in the last 2 videos, I should say, in this SOC Level 1 series that we're in, we covered how to use WireShark and do packet level searches. Now we're going to be investigating, correlating those information, that packet level information, to see the big picture in network traffic, for example, detecting anomalies and malicious activities. For a security analyst, this is a very important skill set. So this is a very vital stop to understand pieces of information spread in packets by applying the knowledge and tool functionality that's available through WireShark. So we're going to be talking about investigating packet level details by synthesizing the analyst knowledge and WireShark functionality for detecting anomalies and odd situations. Prerequisites are the last 2 videos. So the WireShark Basics and the WireShark Packet Operations videos, literally the 2 episodes right before this specific episode inside of the SOC Level 1 2026 playlist. So if you haven't watched those, please go ahead and watch those. The setup is that we have a virtual machine that's assigned to us, and so I've already launched it and it opened in split view. So if I go up here and I do show split view, we'll see this thing, but I'm super zoomed in, so I'm gonna kind of expand that in a new window. I'm gonna shrink this back down, and then I have to zoom out when we actually start using the machine, because even the machine itself is going to be super zoomed in. So we just want to go ahead and make sure that we have all of that set up. And this would be the moment that if you haven't downloaded WireShark already, to go ahead and download it. If you want to download Kali Linux for free, it comes pre-installed with WireShark. So there are a bunch of different ways that you can access this specific tool. And I do encourage you to do that. So if you haven't done it already, pause the video, go ahead and set it up so that you can follow along with the rest of this exercise. You can always obviously just register for TryHackMe as well and get access to their WireShark rooms as well. Do not directly interact with any of the domains and IP addresses in this room. Keep that piece in mind because a lot of them are actually malicious domains and IP addresses, so you do not want to interact with them. This is meant to be done in a secure environment, which is also known as a sandbox environment, which is what it means to actually be inside of a virtual machine like this. Again, this is like super zoomed in, so this isn't what it's going to look like by the end of this when I actually zoom out. But yeah, that's pretty much it. So that's it for our introduction. So let's talk about Nmap scans, detecting and investigating Nmap scans. Okay, this is one of the longer sections. So if you are not familiar with Nmap, my recommendation would be to actually go and watch the Nmap videos from this series. I mean, I have dozens of videos on this channel that we use Nmap through, and I would really recommend that you do that because I'm not going to spend a lot of time explaining the granular details of Nmap in general. There are specific things that we need to know about Nmap to be able to detect these kinds of scans inside of WireShark. So for example, just in case you don't know, Nmap stands for Network Mapper, and it's an industry standard tool for mapping networks, identifying live hosts, discovering services within those hosts, and essentially scanning IP addresses or domain names, finding open ports and the services running on those open ports so that we can use this information as reconnaissance, as intel gathering to be able to develop exploits and hack into the system, right? So it helps us, it's used in multiple contexts. Mainly it's used for network discovery. So when somebody, as a network engineer, if somebody's trying to find out all the variable IP addresses or available IP addresses inside of a network and all the open ports and all of that, they would do that, right? But we can also use it for security and pen testing because on a defensive side, if you find a bunch of open IPs or open ports that aren't being used, you want to shut those down, right? On the pen testing side, if you want to find something to hack, you want to look at all the different open IPs and open ports and see which one would be the easiest one to hack into, so you can gain access to the network. So it's one of the most used network scanners, and a security analyst should identify the network patterns that are created with it, right? So from the perspective of security scanning, this is what we're looking for, are the network patterns. So the most common types of scans are the TCP connect scans, SYN scans, and UDP scans. And we need to understand how Nmap works how Nmap scans so that we can spot any kind of activity on the network. It's impossible to understand this without actually using the correct filters, so these are the filters. So TCP flags in a nutshell, and this is a very kind of like a generic overview, okay? This is not meant to be all-inclusive, so my recommendation would be to study the Nmap videos at least, and if you really want to take it a step further, go study the Network Plus playlist. So as a global level, right, the kind of like the most basic, generic, foundational types of scans that are available inside of Nmap are the TCP scans and the UDP scans, okay? Without really having to do anything, if you just do Nmap and then you give it an IP address, it's going to try to do a full TCP connect scan. And the WireShark filters would be TCP and UDP. When you look at WireShark packets, you'll actually be able to see TCP, Transmission Control Protocol, or UDP, the User Datagram Protocol. So you'll be able to see that inside of the packet. If you only use the SYN flag inside of Nmap, right? If you do lowercase s, uppercase s with the IP address, what that means is that there's going to be tcp.flags equals 2 or tcp.flags.syn equals 1. That's what it would look like if you wanted to do a search for only SYN scans, or if you were looking at the flags that are on a packet inside of WireShark and then you see the flags set, then you would be like, okay, well, this was probably a SYN scan. If there was only an acknowledgement flag that was set, the ACK flag, the rest of the bits are not important. The rest of the bits most likely are not set. So that would be tcp.flags equals 16 or tcp.flags.ack equals 1. Only SYN and acknowledgement are set. So SYN and acknowledgement flags are set. The rest of them are unimportant. So tcp.flags equals 18 or it would be tcp.flags.syn equals 1 and flags ACK equals 1. So I'm sure you can kind of start noticing the patterns with these things, right? It's a little bit less obvious to notice the patterns with the tcp.flags one because there are specific values that are assigned to it. So that part is a little bit difficult. But if you're looking for a specific flag within those TCP options, then you would just do tcp.flags whatever that flag is, and then just do equal 1 so that it is set. And then only RST flag, and then again you can see right here TCP flags dot reset equals 1, only RST and ACK. So again, similar pattern. These things are going to be very repetitive as you start noticing the patterns here. And then the fin flag is set, so you can see that tcp.flags.fin equals 1. So for example, if you wanted to see if the fin flag and the ACK flag and the RST flag was set, you would do tcp.flags.reset equals 1 and .ACK equals 1 and .fin equals 1, right? So you would do 3 filters essentially, and it would scan, or it would look through the packets the way that you wanted it to. Now, TCP connect scans. This is like the most generic scan that is done with Nmap. If you literally just do Nmap and then give it an IP address, by default, it's going to do a TCP connect scan. So this relies on the three-way handshake, also known as the TCP handshake, but it's basically a connection handshake. And we need to understand what that really means and what the implications are. And then once you really understand it, you can actually see how powerful WireShark would be for these kinds of use cases. So it relies on the three-way handshake, which means that the handshake needs to actually finish in order for the connection to be established. It's usually conducted with Nmap -ST or just Nmap just by itself, and then it'll do a connection scan used by non-privileged users. So if you wanted to do a SYN scan, for example, just a SYN scan like the one that we have right here, if you want to do that with Nmap, you actually have to have sudo privileges or root privileges. So non-privileged users can only do a connect scan. Usually has a window size larger than 1,000 bytes, as the request expects some data due to the nature of the protocol. So here's what this means, okay? So we send a SYN packet first. So you'll see a line item inside of the WireShark traffic for the SYN packet. And then we will receive that synchronization has been acknowledged, and then we'll send an acknowledgement packet. And if the last packet is actually sent successfully, then the TCP connection is established. And if that has actually been done, then we can assume that that TCP port is open. This is another one, SYN acknowledgement, and then a reset acknowledgement at the end to destroy the connection, to disconnect from that port. But as long as this is done, then we can say that the TCP port is open. A closed TCP port would be that we send a SYN request, a synchronization request, and we get a reset and an acknowledgement. So it basically says, I acknowledge your request, but I want you to reset because I don't want to connect back to you. And so if that's the case, that means that the port is closed, right? So these are the data that we're looking for inside of WireShark packets to see whether or not a port is open or a port is closed. And of course, Nmap would just display it on our screen for us as we go ahead and do it. It would display it in the terminal. But if you're looking at WireShark traffic specifically, then you're looking for these flags inside of the packets. So here's what we can see right here. This is the open TCP port. So as you can see on the right-hand side inside of these packets, I'll zoom in as soon as my keyboard decides to reconnect here. Here we go. So we have the three sets of, or four. We have 4 packets, right? So this is the source port, and then destination port, and then so this again right here we have the source IP, destination IP. Then the destination IP is right here now because it's responding to us, and then we are responding back to it, and then we'll respond to it again, right? So if we go look at the ports, we can see that our port is trying to connect to secure shell. Secure shell responds, and then we respond back to secure shell on the last 2 lines. And then you can see the flags. Our port is saying, hey, I want to synchronize. Secure shell says, okay, I acknowledge your synchronization. Then we say, all right, cool, I acknowledge your acknowledgement. And now I'm going to also just send the reset because I want to disconnect from you because I don't want to have a full connection established with this. And that's it. So when you see this, even if the last line wasn't available and we just saw these top 3 lines, that means that the port 22 is open. So we try to connect from this port to port 22 responds, and then we respond to it. And that final response, as long as that's actually delivered, then we have that TCP connection established. This is what we call a loud connection, right? So if it was only a SYN scan, right? If it was only a SYN packet that we sent, then it would just be this one line. The last 3 lines wouldn't be available. Now that tends to be quieter, quote unquote, right? Because this right here, you can see a full connection established. We can detect this very easily because hey, there was a full connection established. That's very, very easy to detect. So it tends to be loud in the logs. So what happens though, as a result of this full connection, we can retrieve a lot of data from port 22. For example, the version of the secure shell that's running would most likely be very reliable because we actually were able to connect and we were able to establish a connection, excuse me. If we just sent the SYN scan, it might respond and it might say, hey, yeah, there is this port open that's over here. And we think, right, Nmap would say, I think that this is the version of secure shell that's running on this port, but we can't really rely on it because you can kind of rely. It's just that it's not the most reliance the way that you would get from a TCP connect scan. So you would just get this one packet that's been sent. The port would most likely, if it's not automatically responding with a reset acknowledgement, then we're like, oh, okay, cool. So it's probably open and it's not behind a firewall. So we can guesstimate, we can speculate that it is an open port. It just so happens that we don't get all the detail that we want. So a SYN scan is faster, it's quieter, but it's not as reliable with the data that we retrieve. A TCP connect scan is louder, it's slower because we're waiting for all of these packets to also go traded back and forth. But then at the same time, the data that we receive is more reliable than a SYN scan. If we're looking at the type of activity that implies that the port is closed, so again, we're trying to connect to port FTP right here, and then we can see that we sent the SYN packet to it, and then it responded back to us with reset acknowledgement. So that implies that it's actually closed. This is in an isolated traffic environment, so it's not always easy to spot given patterns in big capture files because there's going to be thousands of lines that you're going to be looking at, and to try to spot these in those thousands of lines, it's very, very difficult. So when they say that this is an isolated traffic, it's like there's only 4 lines that's been, and it doesn't even have a display filter, right? So there's no display filter here. After those 4 lines, that's all we got. So most likely what they did is that they just exported these specific lines and created one little PCAP file just to show that we have an open port, and then this one just to show we have a closed port. So when you're looking at a real capture file, you need to use a generic filter to view the initial anomaly patterns, and then it will be easier to focus on the traffic point, and then the scan patterns in a capture file will be easier. So this is the flags that we will be looking for to see if we actually have a specific connect scan. So TCP flag.syn equals 1, so the SYN flag is set. Acknowledgement equals 0, so that means that it's not set. And TCP window size is greater than 1024. So when you look at that, and this is the filter that we have now here, you can see that that's the filter that they input. And then from here, we have all these different things that are available. So you can see these are all just synchronization requests that have been made, because what? We have the SYN flag is set, acknowledgement flag is not set. So we're just looking for packets that only have the SYN flag. So you can see that it's coming from just these randomized ports, and it's going to very specific ports that are actually used in a lot of environments. These are like default ports that have been set for a lot of different things. 443 is HTTPS, this is secure shell, FTP, I think this is POP3, etc. I haven't memorized all these ports, so I'm not even going to pretend to know that we know what they all are, but that's basically what that looks like. Now the SYN scan, right? So it's done with the lowercase s, uppercase s. This does not rely on the three-way handshake, so we don't need to complete the three-way handshake. It's used by a privileged user because they need to have root privileges. And the size is typically less than or equal to 1,024 bytes. And again, it's not finished. It's not expected to finish, nor is it expected to receive data. The estimation that Nmap makes when it actually gives us data on the screen that's exactly what it's an estimation. It's a guess. It's like a very educated guess that Nmap is giving us. So this is what it looks like. If you have an open TCP port, you send the SYN scan or you send the SYN packet, the system responds with a SYN acknowledgement, and then we respond with a reset. So we don't do the final acknowledgement because we don't want to establish that official connection. Or if we get a SYN sent out and an RST and acknowledgement is sent back, that means that the port is closed. So this is what we're looking at here, right? So again, the port is sending it, or our port is sending it to Secure Shell. Secure Shell says, okay, I acknowledge. And then we say, no, never mind. I don't want to establish the full connection. I just want to make sure that you acknowledge. And if it acknowledges, that means it's open. If it doesn't acknowledge, if it just sends reset, then we know that it's closed, right? As far as the filters that you can use to display this, it would be the flag SYN equals 1. So flag SYN is set, acknowledgement is not set. But now the key element here is that the TCP window size is less than or equal to 1024, whereas the previous one was greater than 1024. So if we go over here, we can now see that we have, again, all the SYN. These are all the SYN packets, synchronization packets that have been sent. The window size is 1024, and then I didn't pay attention to that when we were up here, but if we were to look at that, you can see that the window size is actually much larger than 1024, right? And the TCP window size is exactly the flag that we're trying to filter down just to see what that looks like. UDP scans in a nutshell. These do not require a handshake process because UDP ports are typically the ports that are used for things like streaming. With streaming, and a lot of times you might even be watching this video right now and towards the beginning maybe it was pixelated, or at certain times it could be pixelated. That means that you're not receiving all of the visual data for the video, and that's one of the key elements of UDP. UDP doesn't require the establishment of that connection because it's just going to be streaming a lot of data to you, and that needs speed. It needs speed more than it does the full connection and the slowness of that connection. So you would have a full connection to YouTube, but the video would be presented to you via UDP protocol because that data needs to be sent faster. And so you'll have a full TCP connection to YouTube itself, the YouTube servers, but then you're going to be receiving the data via a UDP port. There's no prompt available for open ports. ICMP error messages are typically what we can expect to get closed ports, and it's done with the SU option inside of Nmap. So open UDP port, there's literally a UDP packet that's sent and we don't get any kind of a response. If there's a closed UDP port, then we'll send the UDP packet, but then you get an ICMP type 3, code message 3, saying that the destination port is unreachable, and that's how we can determine that the port itself is closed. So closed port 69 and open port 68 is what we can see right here. So 69, we sent the request to it, and we got an ICMP response saying it's not reachable, so that means that that port is actually closed. And then we just sent a request to port 68. We didn't get any kind of a response. So just based on that, we can determine that the port is open. The closed ports return ICMP packets. No further information is provided. So can the analyst decide where this error message belongs? The ICMP error message uses the original request as encapsulated data to show the source reason of the packet. Once you expand the section in the packet, you'll see the encapsulated data and the original request as shown here. So they clicked on the ICMP packet, and then we went down here and we looked at the actual packet details, and then we can see if we go and actually click on this user datagram protocol portion, then we can probably pull more information about it. This specific filter shows the UDP scans in a capture file. So ICMP.type equals 3 and .code equals 3. These are all the destination unreachable responses that we got. and then we can't see the ports really. So we can just say that based on these specific responses, there were UDP ports that were closed, but you can always just click on the packet individually itself, and then you can see, okay, well, the destination port on this one, port 69, is the one that responded with being closed. So if I click on one of these and go look at the packet details, we can see which destination port it was that responded unreachable. Detecting suspicious activities in chunked files is easy and a great way to focus on details. So now we're going to use the exercise PCAP file to put our skills into practice against a single capture file and answer these questions below. So wonderful. We get to now officially use the information. So I'm going to zoom out here and we're going to go and look at our, very good, our computer or our virtual machine. I'm just going to open up WireShark, and then in this folder right here would be the exercise PCAP files. So let's move WireShark to the side here. And okay, so instead of doing that, I'm just going to go to File. I'm going to go to Open. And then from here, we're going, this is not the bonus exercise that I'm interested in. I want to find the specific file that has, where's my, there we go, desktop, and then exercise PCAPs. Where is it? Oh, exercise PCAP, there you go. And then from here, we want the exercise. Where's the exercise file? It told me there was an exercise file. Am I missing it? Let me see. Desktop, exercise PCAPs, Nmap, exercise PCAP. Okay, there we go. So Nmap, there we go. Exercise PCAP, got it. Perfect, there it is. All right, so this is the one that we're gonna be using to do our investigation to answer these questions. So the first question is, what is the total number of TCP connect scans? So TCP connect scans, if we just go up here, we can go ahead and determine the type of filter that we can use for it, right? So for TCP connect, we are looking for the SYN, SYN acknowledgement, and acknowledgement to be available to us, and we can just go ahead and find them with the various filters. I want to say the easiest way actually to do this would be to just search for TCP in the filter up here and just press enter. It'll show anything that has to do with the TCP protocol here. And so if I go down here, the displayed number out of 6544 packets, we have 4006 packets that are available for TCP connect scans. So we're just going to try 4006. Let's see if that's actually right. And it's not. Okay, so TCP connect is what we're looking for. So let me, I was trying to see if that was the easy way to get the answer, but it's not, clearly. So let's go ahead and find it. Okay, so the hint was, or well, really not a hint, but we actually did get it in our exercise here where it says the given filter shows the TCP connect scan patterns. So really all we're looking for is the TCP flag scan, flag SYN is set, acknowledgement is not, and then window size is just greater than 1024. So that's basically the element that we're looking for here. So we're just going to go over here and I want to see if I can just paste it. I can't. Can I paste it? I don't think I can. And it just froze on me. So what's going on? The screen is just losing its mind right now. All right, I think I have to manually type it in here. So TCP, TCP, I already forgot. Flags SYN, that's what I'm looking for. TCP flags SYN equals 1 and TCP flags ACK equals 0, and then we have the TCP window size, right? TCP window, window size is with a thing, and it's going to be greater than 1024. There we go. The number of packets displayed are 1000. Perfect. That seems to be a little bit more useful. Excellent. Nice. Which scan type is used to scan the TCP port 80? And so I guess we're doing Nmap specifically. Is that what they're asking? So if I do ST and then I do port equals 80. No, okay. What is it asking me then? That's weird. It's kind of like a weird way to question it. So which scan type is used to scan the TCP port 80? Oh, dude. Oh my God. Wow. It's a lot of times it's so much simpler than I think it is. How many UDP close port messages are there? So we're looking for the one where it says destination unreachable. So we're doing ICMP type equals 3 and ICMP code equals 3. So we're going to go over here, going to delete that to reset everything. And then so we're looking for ICMP like this. Is it typing? There we go. ICMP.type equals 3 and ICMP.code equals 3. And we press enter. There we go. All the destination unreachables. And the display is 1083. So 1083 ports are there. Okay. And which UDP port in the 55 to 70 port range is open? Okay. So we're looking for an UDP port, which would be the open port. It should, do we have it? I don't think we do. So the one that we're looking for is basically the ICMP type is not 3, right? Hold on. Okay, so this question is actually something that we covered in the last episode, which is how to find a range of ports. So there's like it's basically the searching of the squiggly, or like the squiggly whatever, the squiggly bracket. So we're looking for UDP port, right? And then we're looking for, if my computer decides to cooperate, we're looking for UDP port in, and then we're going to do the squiggly right here. And it's 55.70. So that's basically saying I'm searching for a UDP port in that range, which will then give us all of those right here. Okay, cool. So the question is now asking what? Which UDP port is open in that range. So if we go over here, this one was unreachable, right? Destination unreachable. So if we were to look at it, we can see the port itself. So if I click on the unreachable one and then look at the destination ports, so let's go ahead and expand this. Destination port is 67, so that's not open. So 67, that one came back. 69 is also probably not open, right? 69, there we go. We see that right here. So the only one that didn't have a bad response was port 68, because you can see that the UDP data was sent to it and it didn't respond with the unreachable. So it has to be port 68. Cool. Very good. Nicely done. So now we can move on to the ARP poisoning and man in the middle. All right, for a man in the middle attack to work, one of two things basically needs to happen. Either an IP address needs to be inserted in the middle of a traffic transaction, or a MAC address would be inserted in the middle of a traffic transaction. And basically that MAC address or IP address would be the person, the man in the middle that is intercepting, potentially poisoning our traffic. So address resolution protocol, also known as the ARP protocol, is the technology that would be allowing devices to identify themselves, and they do it through a MAC address. Okay, so IP to MAC address table is what you would see if you're analyzing a network table, or an address table, we should say, where it says, okay, you know, this MAC address belonging to this specific laptop belongs to this IP address, or vice versa, right? This IP address belongs to that MAC address, and then that MAC address represents a laptop. And then this other MAC address represents the server, this MAC address represents a cell phone, so on and so forth. And then when those devices, when their physical addresses, their physical identifiers being their MAC addresses, when those physical identifiers connect to a network, they get an IP address. So what happens is when there is a man-in-the-middle attack or an ARP spoofing attack, this involves a network jamming or manipulating by sending malicious ARP packets to the default gateway. The default gateway is your internet router. So in your house, you have a router. It connects you to your internet service provider, AT&T, Cox, whatever, right? So your default gateway connects you to the internet. Think about it like that, right? It's the gateway of you entering the internet. That default gateway is what assigns the IP addresses, or I should say it like this. The subnet, the address of your default gateway, is the same subnet that is the address of your all the devices in your network. I think the easiest way would be to show you like this. So let me see if I can kind of pull this up real quick. Okay, cool. So this is what it looks like. So first and foremost, the subnet that I have chosen is the basic subnet that would be inside of any home, which is this version, what you see right here. So the first three numbers right here represent the first three octets, meaning they each have 8 bits. So 3 times 8 would be 24. So in this subnet, we're saying that we want 24 bits to be accounted for, and then the last one is left at 0. That's the one that we're going to start with, right? That's the one that we're going to, or that's the one that we're going to fill in. So if we go up here, then you'll see like this, and I chose this version, but technically it would actually be 2, because the very first one, that's with the number 1 at the very end of it, that would be the gateway address that's assigned to your router. And then the very last one, or again, not the last one itself, but 255 right here is typically the broadcast address. So the network address in this particular case would be 0. It could be 1 as well. I've seen it usually be 1, but the network address is the gateway address. And then the broadcast address is the 255 that you see right here. That means that's what's broadcasting data. So data that's leaving, it's going to be leaving from that address. And then the usable range would be anything from 1 to 254. So you get a 254 amount of devices, right? So 254 potential hosts can connect to your specific network at a given time, or they could be 254 addresses issued at a given time. Total number would be 256, but there's only 254 that is usable. If you were to look at it in a binary, this is 8 bits, right? So 8 ones, 8 ones, 8 ones, and then 8 zeros, leaving off that last set that we could actually fill in. So this is what it looks like, right? This is a basic network inside of a home. This is what it looks like. So connecting it back to this, the default gateway is the one, that very first one right here, right? So what happens here is that there's an attack that involves some kind of packets that are sent to your default gateway, and they typically would have a fake address resolution protocol address, so a fake MAC address. So the ultimate aim is to manipulate the IP to MAC address table and sniff the traffic of the target host. That's basically the goal here for whoever is going to be capturing the traffic. I went into way too much of an explanation in this first paragraph, because there's going to be more information that we can use for this. So there are a variety of tools to conduct ARP attacks. A lot of these things are pre-coded, pre-written, and ready for you to use, and a lot of them are free. And the mindset of the attack is static, so it's easy to detect such an attack by knowing the ARP protocol and the WireShark skills that would be necessary. So ARP analysis in a nutshell: it works on your local network. It enables communication between MAC addresses. It's not a secure protocol. It's not a routable protocol. It doesn't have an authentication function, and common patterns are request and response, announcement, and gratuitous packets. Before investigating, we can look at some legitimate and suspicious ARP packets so we can kind of see the difference. The legit requests should be similar to each other. Broadcast request that asks if anybody's available, and the host and IP address, and a reply from the host that says the particular IP address is actually used. So, the host will say, like my computer will say, hey, who has this IP address? And then it goes and refers to this table, this IP address table right here. And then it says, oh, this MAC address hosts this IP address. And then it'll respond back to me. That's basically what it is. So the global search would be ARP, and then the options that we have here. So opcode 1 is the ARP request. Opcode 2 is the response, as you can see right here. And then hunt, ARP scanning, possible ARP poisoning detection. So what you can see right here, so we have the destination MAC right here. That's what it could be. Usually that's not what it looks like. It's like a variety of alphanumeric characters, but that's what it kind of, the format looks like that. ARP duplicate address detected, or ARP duplicate address frame, and then the possible ARP flooding. So you're looking for ARP and the ARP code 1, and the ARP source MAC address would be the target MAC address. So you would use that as a full query. So just to kind of demonstrate this a little bit easier. So ARP protocol, right? So we see this on the right hand side. So it says the source MAC address, this thing right here. The destination, if it's like this, that means we don't know who the destination MAC address is. So it's sending it to every device in the network, and it's saying, hey, who has this IP address, tell this IP address. And so the 125 at the end right here belongs to the source. So it's saying who has this, tell that IP. And so the response would be, yeah, 192.168 is at that IP, at that MAC address. And then now we can see that that MAC address is now filled in. So the destination here that's blank is now filled in. And now the response is, yeah, this belongs to that specific MAC address. So that's what that looks like. And then you can always look at that in the address resolution protocol details down here as well. So the sender MAC address is this, sender IP address is that, target MAC address is blank because we don't know what the MAC address is yet, and the target IP address is that IP. So we're just saying, hey, what device is connected to that IP address? The reply would then say, yeah, this is me. So this is the sender's MAC address now because this was the one that was blank, and it belongs to the IP address that we targeted. And so it's saying, hey, that's me, that's my MAC address, right? Or that's my IP address, right? The MAC address is saying, yeah, that's my IP address. So the machine is basically saying, yeah, that's me, that's the IP address assigned to me. So the suspicious situation means that there are two different ARP responses. So there's a conflict for a particular IP address. In that case, WireShark Expert Info tab warns the analyst. However, it only shows the second occurrence of the duplicate value to highlight the conflict. Therefore, identifying the malicious packet from the legitimate one is the analyst's challenge. A possible IP spoofing could look like this. So same thing, right? So we went and said, hey, who has this IP address? Tell me. And then there's two responses from the IP, and they have two different MAC addresses. So there are two machines raising its hand and saying, yeah, that's me. That's my IP address. And now it's up to you to be like, well, that's kind of impossible. It can't be possible for the same IP address to be on two different MAC addresses. So one of you is an imposter. So knowing the network architecture and inspecting the traffic for specific time can help the anomaly. You should take notes of the findings before going further. This will help you organize and make it easier to correlate further findings. So look at the given picture. There's a conflict. The MAC address ends, crafted an ARP request saying that that's me. That this is it, the one ending in B4 says that, yeah, I'm the one with the IP of 11. So possible IP address match, one matched from one specific MAC address, this one right here. That seems to be the legitimate one. The spoofing is saying that MAC 1 and MAC 2 are both saying, yeah, that's me. And it's like, well, that's not possible. So the ARP flooding attempt could potentially be this guy right here, the second one, saying that, yeah, I think that's me. Or that this is me. And now it's up to us to be like, okay, well, we have to determine which one of these guys is actually correct, which is essentially the challenge that is presented to us. So now we need to inspect the traffic to spot any other anomalies. So we can see right here where we have the source MAC address, right? The one ending in B4, the one that we think is malicious, is replying to a bunch of empty ones as it seems. And the question that it's asking is who has that IP address, tell 125, I think that's the legitimate one, right? So the B4 is the legitimate one. Yeah, the B4 is the legitimate one. So the B4 is the one that's communicating with the rest of the network saying who has this, who has this, who has this, and tell the IP that's ending in 125, right? And then in the first response immediately, there was the IP address 11 saying that I'm at this MAC address at F4, and it's responding, and then the rest of them are being sent to all these other IP addresses on the network to try to connect and try to figure it out. So there needs to be, it's really not helping us much in this particular case because it's saying that the case is split into multiple capture files to make the investigation easier. So I think that's probably what they're saying for our exercise. So it's evident that there's an anomaly. Security analysts can't ignore a flood of ARP requests, which is what you see right here. All these ARP requests coming in, you can't ignore that. This could be malicious activity, scan, or network problems. There's a new anomaly. The MAC address that ends with B4 crafted multiple ARP requests with the 125 IP address. So let's focus on the source. So possible IP address 1 announced from a MAC address, which is the B24, which I thought was the legit, but it might be bad, I guess. It might be like a bad address. And so, whoops, let's go and let's make sure that we renew our machine so it doesn't kick us out, because that is really annoying if it does. So let me go up here and add an hour. I stepped away from my computer for a bit, so the timer kind of tripped out on me. And so let's go back here. So where were we? We were over here. No, we were over here. So possible IP address, saying, the IP address announced from a MAC address from, 1.25 is saying that it's from B4 MAC. Possible ARP spoofing, two MAC addresses claim the same IP address of 1.1 at the end. And these were the two MAC addresses, B4 and F4. So MAC address 2, B4, is actually this one. So it's literally the same one that's also claiming to be at 1.25. It's also claiming to be at 1.1. And then MAC address 1 replying is the one with F4. So the MAC address that ends with B4 claims to have a different and new IP address. So now it's saying that I'm at 1.1, when originally it was the one saying that it's at 1.25. And the MAC address that ends with B4 crafted multiple ARP requests against a range of IP addresses, which what we saw was that possible ARP flooding attempt. So it's evident that the MAC address that ends with B4 owns the 125 IP and crafted suspicious ARP requests against a range of IPs. It's also claiming to have possible gateway addresses as well, so we can look at other protocols to spot the reflection of this. So we'll go right here and look at the HTTP protocol. So it's that 1.25 is not even in this list. So it's saying, what is it saying? It's saying, the 1.12 going to this IP address is making a request to get the login page. And then that IP address is now responding with a continuation. And so 1.12 is now saying get style and get images and all those things as well. And then the 493 is responding with continuation. So this traffic, everything looks normal, so there's no linked information with the previous findings. So let's add the MAC address in the column. So if we go over here now, and if we look at the 112, and then going and looking at these, and so the F4 IP address or the F4 MAC address is the one that we saw previously. And then this one, look at this, the MAC address is all going to the B4. Even though the destination is two different IP addresses, technically, the destination on this is the same MAC address. And so it's saying, or it's getting as a response, all of the stuff from the website. So the MAC address that ends with B4 is the destination of all the HTTP packets. It's evident that there's a man in the middle. So all of these packets, no matter what is the interaction between the IP addresses, all of those packets are being sent to this, and this person is intercepting all of those things. So all the traffic that's linked to 1.12 is forwarded to the malicious host. So let's summarize our findings. So IP to MAC matches. So 3 IP addresses are matching to this one MAC address, it seems, or I should say 3 IP to MAC address matches. So there's three different ones. My apologies. So we have B4 ending in 1.25. F4 is ending in 1.1. And then A8 is ending in 1.12. The attacker created the noise with the ARP packets. So the B4 MAC address is connecting to 1.25. That's the one that did all of the ARP attempts, the ARP address requests. And then the router and the gateway, our MAC address, which is F4 in this case, responding and saying that it's 1.1, because remember we looked at the calculator, and typically, I know in this particular case it says 0, but typically this was my mistake, because I actually went over here and I said that it was 1.1. So if I went and did 5, for example, in this particular case, the network address, it's still at 0, but really, if you actually go and do ifconfig, or if you do ipconfig on your computer, you should get a response of the one that ends with .1 should be your gateway address. It should be your router's address. The attacker sniffed all the traffic of our victim, which happens to be in this particular case 1.12, and F4 being the router. So the router itself was the one that was sending all of these requests out to get those HTML, for the HTTP protocols to get website information, because somebody was using it, right? Some other IP address was interacting with a website and trying to get a login page, and from that login page the style sheet was brought, and then images and the logo and everything was brought. So the login page was loading, but all of that was actually being sent to this specific MAC address right here, which is the one that is intercepting all of the traffic. So it seems like these are the sources that are actually requesting it, and that would be the case, where it's like, well, these are the sources that should also be the ones that are receiving all of the data from this website. But when we look at the source MAC addresses and the destination MAC addresses, they don't line up. So this is where the requests are being made, but all of them are being sent to that intercepting MAC address. So detecting these bits and bits of information in big capture files is challenging. So in real life cases, you won't have tailored data ready for investigation. You need to have the analyst mindset, and we need to obviously use a variety of different tactics to filter traffic down. There are always alternative solutions. The solution type and approach depend on the analyst knowledge and skill level. Detecting suspicious activities is what we're going to be doing. So we're going to go into the ARP folder now and pull the exercise file to be able to answer these questions. So let me go ahead and zoom back out here, and let's go into our computer. We are now in this location, so we can just kind of, I guess I can open, I don't know if it's going to open multiple instances. So I'm just going to close it, and I'm going to open the PCAP location. We're going to go into ARP, and then we're going to open up the exercise PCAP file. So we'll do it like that. So right now we have a total of 2,866 packets. So let's look at question number 1. It says, what is the number of ARP requests crafted by the attacker? So to be able to get ARP requests, we need to go ahead and pull up a specific filter. Since we're only interested in the ARP requests that are crafted by the attacker, we basically need to find all of the packets that are from this specific MAC address. And so if we open this file right here, we can see, so I'm going to remove this filter real quick. Basically what it looks like when you load the file in general is you'll have, why isn't this loading? So you'll have this, what it looks like at the very, very top. So we have SSDP protocol and an ARP resolution protocol. And then we have all these requests, right? Who has this, who has this, who has this. So we can see that the MAC address here doesn't look exactly like what we saw in the screenshots. But what we can do is we can right click on this specific portion and then apply it as a filter. And then it actually creates this port for us. So it says ethernet.source equals that specific MAC address. And so then once we do this, we can actually just see all of the requests being made by this specific MAC address. And there's a lot of them. So it says 1450 are displayed. These seem to be all of the requests made, but we have a 3-digit answer by this specific person, or I should say, for that specific question, we have a 3-digit answer. So that doesn't seem to be the response that we're looking for. Okay, so here's the glitch right here. So when I just do that Ethernet source, if I scroll all the way down, all of a sudden we see that there's a bunch of TCP packets, and there's a lot of different protocols that are presented to this that are not ARP protocols. So we're specifically looking for ARP protocols. So another way that we can filter this down a little bit would be to just say and ARP, to just make sure that the protocol itself is only ARP. Now in this case, if I scroll down, I should only see ARP protocols, and then we can see that they're sent to a variety of different MAC addresses, but it's all from that source. So what we're also trying to do is we need to go ahead and figure out it says the ARP request crafted by the attacker. It could technically be all of them, but there's also all these other ones that are sent to a variety of different addresses. So this can be the fact after the requests have already been done, and now it's actually communicating with a variety of different machines. So we can go ahead and apply the broadcast as a filter, which would end up being Ethernet destination equals the Fs. So if I do Ethernet dot source equals so actually let's see if I can do it like this. This might be easier. So I'm going to cut this piece right here, and hopefully this will work better. So if I cut that, can I cut that? I don't think I can cut that. There you go, I cut it. Okay, perfect. So if I do this, if I go ahead and use this as a filter, and then we can say and ethernet.dst equals the F's right there. So the F's right there, and we'll do ARP. So if we do that, we should get a shorter response. So we can see a bunch of these things right here. So it says displayed of 256. If I get rid of this, let's see what's there. It's also 256. Okay, let's try 256. Let's see if that's the answer. It is not the answer. Okay, so I think we're getting closer though. At least it's down to 3 digits. So let me see what else could be potentially the filter. So I went through this whole thing, and apparently the screen wasn't even recording, and I found out until I got to the end of the next section. So the end of this section is when I found out that the screen wasn't recording. So we're gonna go back and find all of these answers for you one more time, and then I'm gonna record the next section one more time. Unbelievable. Okay, so the answer for this is actually 284. Now, the way that we find that, I'm losing my mind right now. Okay, so the way that we find that is that we need to use a filter that was previously given to us at the very, very top right here to be able to find those addresses. So it's right here. So we're looking for this. Instead of doing the Ethernet destination or Ethernet source, we're actually looking for this version of the filter, which is that ARP DST HW MAC version. So we're going to go ahead and use that as the filter. And so hopefully I can paste it, which it seems like I can't. And let me just make sure that this is still recording, because now I'm super paranoid here. So it's basically ARP, right? DST.HW MAC. That's the one that we're looking for the zeros. So it would be 0 like this, right? So that's that one. And then we're going to combine it with the other one. There we go. So now we have the actual packet that we're looking for, because it's basically the source is going to be the attacker, and then the destination is the network router that he's trying to communicate with. And then so now we get with 284 as the result that we have, which is our answer for that first question, right? So you're using the ARP.DST.HW-MAC filter instead of the Ethernet.destination and source. And then it says, what is the number of packets received by the attacker? So in this case, we're looking at HTTP packets, right? So the destination now in this case, so now we can go and use the other filter, right? So let me see if I can actually do cut and paste in this version right here, at least. Hopefully we can do that. So in this case, the Ethernet destination, right, is going to be our attacker's MAC address, and we just want the HTTP protocol to show up just so we can see the number of packets for that. And so we can see down here that the number of packets that were received by that person are 90. So that's going to be answer number 2 right here, which is the number of packets received by the attacker. So making some decent progress here. Next question is, what is the number of sniffed username and password entries? And this one was actually a little bit tricky. So thankfully, I've already gone through it, so I can kind of guide you through that. So basically what we're looking for is, number 1, we want to actually see from all of these packets, right? So from all of these packets, we want to kind of see what potential page would give us some information. So if we scroll up here, there's a specific page called the userinfo.php page. And if we go to the packet details and look at the URL encoded portion of the packet, we'll see that there are 2 fields here. We have the uname and the password. So the username and the password. And so the uname is a key. The value would be the username or the password, right? So what we're looking for specifically is something called URL encoding. So one of the things that we want to do is we want to keep this specific filter here. So we actually want this to stay. So we're just going to put this inside of parentheses. And then we're going to add a specific element to it, which basically says and URL. And then you can see the autofill helps us here. So it's URL encoded form. And then if I do dot, I'll either get key or value. So I'm looking for a key, and the key needs to be the one that includes pass in it. So I'm looking for the one that actually has pass in it, because the uname is going to show up in a lot of different cases. So that narrows it down to just 6 packets, as we can see right here displayed. So now we have 6 packets, which ends up being the answer to this question. So now we just need to go through those 6 packets to find client 986's password. So I think it was this one. So there you go. So client 986, the password is client not here. So super simple and straightforward so far. And then the last question, this one took me longer than it should have. And it was basically because I was trying to find the comments of the entire packets, which can be done technically. There was a way that I knew that we could do it. But basically, there are 2 ways to look at comments in general, right? So you want to go to, I think it was statistics or no, analyze. It was analyze, and then you're looking at expert information. And in here, there's usually comments somewhere. Like there's something that you can pull from the comments. And if I go and do client, for example, that's where it should be, but technically it's not there. So that's definitely not what we're looking for. So the way that I found it is I just went to edit and I did Control F or find. And then I'm looking for the packet details. Inside of the packet details, I'm just looking for client 354. That's basically the one that I want. So I'm going to click on find, and then it's going to find the packet for me. It's packet 2320. And if we go to the data in the packet details, we can see that client name client 3454 has a comment of nice work in it. So that way we were able to find the comment. And there we go. And that's the comment for that packet. So that's how we found all of those answers. Now, I'm going to redo the entire lecture portion of this next section. Okay, this should also be a little bit quicker and easier because I've already done the lecture. So I can kind of summarize most of this stuff for you. So identifying hosts is a very important skill set. And as you can kind of tell, we went from looking at, the protocols, we looked at MAC addresses, IP addresses, all those things. So one of the key things that we want to do now is we want to actually find the host inside of an environment. So what's really cool about this, it's kind of like a pro and a con kind of a thing. It's a 2 sides to the coin, or like the edge of the sword, like double-edged sword, one of those things. So in an environment, in the enterprise environment, what happens is that companies usually will have some kind of a pattern, right? So it'll be something like, I don't know, NSB dash Hank Ackerson, something along those lines, where it's like there's a pattern, right? So it can make it easier to follow the inventory, but it can also make it a little bit difficult for us as analysts, because the attacker can now clone that pattern and then live in our network, because now they know what our patterns for usernames look like, for host names look like. So we need to be able to obviously avoid that, but we need to also be able to identify actual usernames by a variety of different protocols. So the first one is the DHCP protocol, Dynamic Host Configuration Protocol. Then we have Network Basic Input Output System, and then we have Kerberos. And all of these are used for host and user identification. So first, DHCP. DHCP is the protocol that allows IP addresses to dynamically be issued to the devices in your network. So instead of somebody sitting there and assigning IP addresses one by one to every computer that comes in, or every cell phone that comes in, imagine if you had to do that for everybody that tries to connect to the Wi-Fi in your house, right? So there's a protocol that automatically assigns IP addresses to the devices that connect to the router, to our network. DHCP or BootP would be the global search inside of WireShark. And then we have a few different ways that we can track these things down. So there are DHCP requests, acknowledgements, and NAC. And I want to say it's like not acknowledgement, or like maybe an error is what NAC would be. So DHCP option, DHCP equals 3 is the option for request, and option 5 is for acknowledgements, and NAC, which is all the errors, would be option 6. Option 53 is the only one that actually has predefined static values. So we would, for all of our investigations, we would filter the packet type first, and then you filter the rest of it by applying a column and then using something like contains or matches, which we did a lot of in the last video, in the last episode. So for this, for example, so let's say DHCP request, right? So option 12 is the host name, 50 would be the requested IP, 51 would be the requested IP lease time, and then 61 would be the client MAC address. So if I wanted to do host name, for example, I can do host name contains, and then whatever the name of the keyword is that I think it would contain. For acknowledgement, similar, right? So option 15 is domain, 51 is assigned IP lease time. So option domain name contains keyword. And for non-acknowledgement, because it's error messages and there are really no like patterns, usually there are no patterns in error messages. So what we're really just going to look for is we're going to filter just for the denied or for the errors, which in this case would be option 6. So DHCP option 6 would end up giving us all of the NAC packets, and then from there we can kind of read through or filter through the messages to try to find what we're looking for. So just as an example of what we're kind of trying to find is if we go inside of if we search for DHCP protocol, as you can see right here, and then click on any of the packets and we go to the packet details, we can see now the host name option, right? So DHCP message type, client identifier, and then option 12 right here has the host name, and then we can actually see the host name in there. So that's one way of identifying the hosts. The next one would be the network basic input output system, which is for allowing applications on different computers to communicate with each other. NBNS would be the global filter, and then we're looking for something like nbns.name contains the keyword, for example, and then we'll be able to find it. So NBNS, again, as the global filter, we click on any of these guys, and then we go down here, and then now we can see that the name for this Xerox machine right here is the conv_Xerox, for example. So if we're looking for, NBNS name contains Xerox, we should hopefully be able to find, I guess, all the printers, maybe. That's probably what it would be. And then we have Kerberos analysis. So Kerberos is unique and native to Microsoft Windows, and it allows for service requests. I'm not going to go into the details of it. We've covered this a lot in different videos. So if you don't know it, it's basically to grant tickets for identification and then to grant tickets for access. That's what Kerberos is. It's like a ticket granting system. So we can search for Kerberos packets specifically by searching for Kerberos globally and then looking at things like, the CNAME string contains a keyword or the CNAME string contains something, but I don't want it to contain a $sign because the $sign would be the host name and I want to find usernames. So this is what we talked about in the last video as well. If you put a exclamation mark in front of your query right here, you're saying not this. So it's like, I want this, but I don't want these, is what that query is essentially saying. And Kerberos has a lot of different extensions to it. So if you just type Kerberos and then do a dot, which is what we did with the URL encoded thing, the autofill will help you out a lot with that. So for grabbing low-hanging fruit, we can do the protocol version, the domain name for the generated ticket, service and domain name for the generated ticket, addresses, things like that. So Kerberos.pvno equals 5, Kerberos.realm contains .org in it, Kerberos sname string contains KRBTG, something like that. So the addresses information is only available in request packets. Just keep that in mind. This piece right here, it's only available in request packets. So you would need to combine this with Kerberos requests, right? That's the piece that we would need to kind of hone in on if we're looking for that. This is an example. So if we do Kerberos as the global search, click on any of the packets, look at the details, we can see the CNAME, the name of the device in this case is, or the user, I think, in this case would be KRB5NT principal. So that's how we can filter those down. So now we can go ahead. Let me make sure I'm still recording. Okay, great. We're still recording. So now we can go ahead and zoom out and go ahead and launch our machine and use our exercise files. So in this case, we're looking for the NetBIOS Kerberos folder, and we're going to use DHCP NetBIOS for the questions 1 to 3, and then Kerberos PCAP we're going to use for questions 4 and 5. So let's go and find DHCP NetBIOS. Let me tell you, man, I was pretty upset that it was not recording and I had to do that whole thing all over again. It wasn't as bad as what it was in my mind, but I was pretty pissed, let me tell you. All right, okay, so what is the MAC address of the host Galaxy A30? So we're looking for the host Galaxy A30, and it could be anything. So we could be looking for any type of protocol to search for that host name. So I'm going to do the cheat real quick. I'm looking for Galaxy A30. So I'm gonna just go here. I'm gonna do edit, and I'm gonna find a packet, and then let's see if the string contains Galaxy A30 in it. Let's see if we can find one specific to that, and see if we can find the MAC address for it, because that would be pretty handy if we could actually do that. Okay, so there was nothing for that, so that shortcut didn't work. So we can use any of the filters that we had previously, right? So you can pretty much go through anything that you want from the list of filters that we got over here. So if we start from the top, if we're looking for a host name, for example, right? So DHCP request, the option is dhcp.option.hostname contains something like that. So if I go over there and I'm looking for a MAC address of Galaxy A30, I can do exactly that. I can do DHCP. Let me zoom in here just so you can kind of see what's going on, because this is also really, really handy if you do this, right? So if you actually do DHCP and then do dot, right? Now there's a bunch of stuff. And so we're going to do option, right? Dot H, and then boom, host name is right there. And then we're going to say it contains Galaxy A30. And let's see what we can find with this now. And let's see if that actually gives us something. Hopefully it does. Okay, so Galaxy A30 doesn't give me anything. So what if we do just Galaxy? So let's go do that. Contains Galaxy. Let's see if that gives me, oh, wonderful. Look at that. So we got a couple right here. All right, fancy. So we are looking for, what is it? We're looking for the MAC address, right? The host that has Galaxy A30. So we can just go one by one to these guys. And I mean, the source for this one is the network router, and the destination seems to be the broadcast IP address. So that one's fine. So the third one might have some interesting info for us. So if we go over here and see if we can find option name, host name, wonderful. And host name is Anthony S Galaxy A30S. Okay, that's very detailed. So let's see if I can just type, oh, MAC address is what I'm looking for. What am I doing, buddy? Okay, so client MAC address is what we're looking for here, which is the 9A81. So let's see if we can copy the MAC address. Let's see. Sweet. Okay, so it did copy the MAC address. I just wasn't sure. I usually just paste it into my browser just to make sure it actually worked. And so it did in this particular case. Wonderful. Okay, great. So question 2, it says, how many NetBIOS registration requests does the Level JM workstation have? So we're looking for NetBIOS registration requests. So if we go to the NetBIOS filters, it basically has just one. So NBNS name. So we're looking for that. So we're going to go ahead and delete all of those right there, and we're going to do nbns.name contains livaljm, livaljm. Okay, so there we go. So we have this, and we're looking for a request, I guess. So let me see. What was the option for that? Is there an option for requests? Okay, after a quick little Google, we see right here nbns.opcode equals 5 is filtering for the NetBIOS registration request. So that's what I am most interested in. So I'm going to go ahead and do one of these things right here. So we're going to do a, what is it? Close parentheses, and then we're going to do an open parentheses at the beginning of it. And then we're going to go right here. And I got to keep double checking that the recording is going, because that really just, and okay, nbns dot, and if we could also do this as well, but I wouldn't know what to look for. So we have to do nbns dot opcode. Isn't that what it was? nbns dot opcode. What is it? nbns dot opcode. Yeah. nbns dot opcode equals 5. I thought that would, or maybe nbns. I see. Okay, so there we go. nbns flags.opcode equals 5. Also, so if you know, when you do research like this, it doesn't actually help you. So what you can do is you can go to, I want to say statistics, no, analyze display filter expression. So display filter expression will open up this window for you, okay? And then inside of this window, you can start looking for a number of different things. So for example, if I want to search for NBNS, then it will bring up NBNS for me on the list of filters. I can expand it, and now I have a bunch of stuff that's in here. And then so I could be looking for the flags opcode, right? So opcode is what I'm looking for specifically. So I could do that. I could type opcode, and then it'll bring up a bunch of things, because opcode is probably a variety of different things. So then you can go right here, right? So I selected opcode, and then it says is present, so it does equal, and then we're going right here. We're looking for request, I guess, registry, registration, wait for acknowledgement, refresh, etc. So it doesn't show me actually what the, I guess registration request would be the one that we're asking for. So it's not looking for request. We're looking for registration specifically. So anyways, we're looking for opcode 5, just to kind of speed that up. So opcode 5, and then we have Livel JM also included in it. So the answer seems to be that there are 16 packets. Let's make sure we're still recording. Okay, great, we're still recording. So the answer is 16. Yes, excellent. So which host requested the IP address of 172 yada yada yada? So I'm gonna try to see if I can copy this. It never works when I try to do the copy. For whatever reason, I can't copy from here and paste it into WireShark, but whatever. Okay. So the question is what host requested the IP address? So we are looking for host requesting IP address would most likely be DHCP, so Dynamic Host Configuration Protocol. So DHCP option, and then what are we doing? Option request, right? Requested IP address. There we go. So option requested IP address. Excellent. And then we're going to do equals and moment of truth. Let's see if we can paste. We can't paste. Okay, so I will open this up. So 172.116.13.85. Okay, so there we go. So that's what it was, right? So it says which host requested that. And okay, we only have one. We have one packet that was filtered. So we can just go down here and try to find the host name to see what we can actually find for this here. And it's right there. So it's the host name option. Galaxy A12 would be the answer. Galaxy-A12. Perfect. And next one is, what is the IP address of the user U5? Enter the address in defanged format. It doesn't really give us much to be able to find U5 IP address or U5 user. Wow. Okay, so I mean, there's a bunch of things we could do here. What's down here that we can try to find a username? So CNAME string contains the username. Okay, so let's try this one. Let's try this filter. Kerberos.CNAME string contains U5. That is so generic. It's 2 letters, man. Kerberos.CNAME string. There we go. And then it contains U5. Good Lord. There has to be like a bunch of them. It can't be a few. I can't imagine that it only has a few. And we're literally searching through 180,000 packets. That's the other thing that's kind of just like driving me insane. It's not working though. Nothing is loading. So this is an issue for us. So Kerberos CNAME string contains U5 isn't loading anything for me. Oh, it's because I'm looking in the wrong packet. Oh my gosh. Okay, so I need to go and load the other packet capture file because we're officially on question 4. Yeah. Oh my God. I would have spent so much time not realizing that I'm in the wrong thing. So let's close this out and let's go into the Kerberos one. Okay, so since we're in the Kerberos one, we definitely need to use Kerberos. So Kerberos.CNAME string, there we go, it's right there. Give it to me. CNAME string right there. That's the last one that I used. Contains U5. There we go. I was like, why isn't it loading anything for me? There's only 82 packets in this one for us to use too, so that should be pretty nice. Okay, so it says which one, what? It says which one, what is the IP address of the user with U5? So IP address of the user with U5. So let's see. Okay, really, there's only 2 IP addresses that are here for us to look at. Or yeah, 2 or 3. There are like 2 or 3 IP addresses for us to look at. The one that stands out the most is the one that ends in 1, because that is the one, in my opinion, that would be the router, the gateway. And so I believe that would be the one that would most likely be kind of requesting usernames, maybe. I think it's not, I don't know if it's the best logic, right? So anyways, we can see what we can find over here, because all of these things contain U5. That's the other issue, is that like all of their, most likely all of their usernames would contain U5, I would assume. So let's see what I can find here, because request body, there we go. And then the name would be Denny DC. Okay, no, actually, interestingly enough, it is not the case. Okay, so really the packet details, as far as I'm seeing, doesn't include anything that can actually help us with this. And instead of trying to guess, the only other way that I can think of is if we look at the hexadecimal point right here. So this is the binary, we have hexadecimal. We can see that U5 is in here. So among all of the gibberish, it seems to be that U5 is in there. So it would be, in my guess, 10.5.3.1. So let's go defang it real quick. So CyberChef, oh, I already have CyberChef saved on my toolbar. Should also be saving it. So we are going to defang something. So we're defanging IP address, and it's 10.531 basically. So 10.531. That's it. And the defanged version would be this. That's basically what that means. So we're going to copy that, and we're going to go over here. I'm going to paste it. Let's see if that's the answer. Why is it doing this? What the heck is this? Enter the defanged format. Literally, that's exactly what I did. I don't understand why you're doing this to me. Oh, yay, I found it. My God. Okay, so this is actually from 10.1.12.2. That's actually the one that has U5 in the CNAME value. And it's literally U5. There's nothing else attached to it. And it's Denny DC. So I think I was on the right path. It's just that I was looking at it instead of looking at the destination, I was looking at the source for this one. And it's actually supposed to be the destination. So 10.1.12.2, I think, is the IP address. I apologize for not having like more solid responses for you on these things. But I feel like that's the right one. Yeah, okay, great. All right, what is the host name of the available host in the Kerberos packets? So we are now looking for the last one right here. So the available host in the Kerberos packets. There should be a few different ways that we can do this. So essentially what we're looking for is this value. So where is it? It's this thing right here, this piece. We're looking for that specific value, this CNAME string, because that's the one that actually has the usernames in it. So what we can do technically, I think, because there's a way that we can apply these things as columns. So if I click on that, and if I apply as there you go, apply as column. And there we go. Now we have a uname string. So now we have the CNAME string, excuse me. So the CNAME string is now there. So if we get rid of our filters, and if we see which one actually has a value, so DSXP1 $, that seems to be the only one that actually has like a real value, because the rest of them are just BS really. So what was it? It was XP1 $. So XP1 $. Host name, especially because it has a $sign in it, right? So host name, there we go. Yeah. Host name has a $sign in it. So we could have technically even done this, right? We could have even done this piece right here, where we could have gone where right here where it says it doesn't include the $, we could have actually gone and just done that, because that actually says literally to avoid the $, value that ends is a host name. So we're looking for a host name. So we could have just gone over here and we could have done the Kerberos, right, .cname, all of that. So that thing. Now, instead of it saying U5, we're just looking for the one that actually has a $, in it. There you go. And that's the only one. That's the only one that actually has a $, in it. Solid. Okay, excellent. Progress has been made. And let's make sure we're still recording. We are still recording. Fantastic. All right. Moving on to tunneling traffic, DNS, and ICMP. Okay, traffic tunneling is also known as port forwarding. So where you forward the traffic from one port to another, and you then create a digital tunnel when you do that. So it transfers the data and the resources in a secure method to network segments and zones, and it can be used for internet to provide to private networks, so internet to private networks and private networks to internet. So this is the flow of the data. So either it's coming from the internet to our private network, or it's leaving our private network to go to the internet. There's an encapsulation process that hides the data, so the transfer data appears natural for the case, but it contains private data packets and transfers them to the final destination securely. This provides anonymity, it provides traffic security. Therefore, it is highly used by enterprise networks. However, as it gives a significant level of encryption, attackers use tunneling to bypass security perimeters using the standard and trusted protocols that are used every day, like ICMP or DNS. So for us to be able to have the ability to spot these types of anomalies is very important. So ICMP analysis, ICMP is Internet Control Message Protocol. It's designed for diagnosing and reporting network communication issues. It's used in error reporting and testing. It's a trusted network layer protocol because it's used a lot for regular network administration or network engineering. So sometimes it's actually used for DOS attacks, denial of service attacks. So adversaries also use it in data exfiltration and C2 tunneling activities. So this is one of those things that there's something called LOL binaries. It's separate from this, but it's similar in like the same spirit. So LOL binaries stands for living off the land binaries. And when somebody hacks into a machine, instead of downloading their exploits onto the machine or instead of coding something new, they use the binaries that already exist on that machine to do their work, to do their malicious activities. And because those binaries already exist on the machine, it's easy to kind of get them past the first layer of security or inexperienced eyes, like the eyes of somebody who doesn't have a lot of experience. So this is a similar concept where we're using a port or a protocol that's used regularly, and then it's going to be used for malicious activities. And this is what we're trying to keep an eye out for and really investigate. So in a nutshell, the tunneling, ICMP tunneling attacks are anomalies appearing or starting after a malware execution or vulnerability exploitation. So somebody uses the LOL binaries, executes an exploit, and then immediately after on the timeline, you see that, okay, there's now a amount of traffic that's leaving our network and there's data that's leaving the network. So as the ICMP packets can transfer an additional data payload, adversaries use this section to exfiltrate data and establish a C2 connection. It could be TCP, HTTP, SSH. As the protocol provides a great opportunity to carry extra data, it also has disadvantages, and most networks block custom packets or require admin privileges to create custom ICMP packets. A large amount of this type of traffic are indicators of ICMP tunneling, so the adversaries could create custom packets that match the regular packets, which is 64 bytes. So it's still cumbersome to detect these tunneling activities. However, a security analyst should know the normal and abnormal abnormal to spot anomaly and escalate for further analysis. So here are our filters. We have the global search for ICMP. You just put that into WireShark. Then the options for grabbing low-hanging fruit, it's the packet length, the destination address, and encapsulated protocol sign. So for example, data.len for length greater than 64 and ICMP as the global variable. So this is what you see right here when somebody actually uses that. And then so we can see the protocol's ICMP, the length is greater than 64. And then, it's basically replies and requests, because a lot of times it is just a ping that is gone through ICMP. But then when we kind of look at it a little bit further, we can see where it's going. So the destination address as to where it's going is crucial, right? So the one that is, I want to say the one that is making the request is the one that we need to worry about, because that's the remote location that's making the request, and then ours is sending the reply to him, or to them, I should say. So that is, this is the filter to be able to detect ICMP anomalies potentially, right? Then we have DNS analysis. So the domain name system is designed to translate or convert IP domain addresses to actual IP addresses. So this is another one of those things, right? So the domain name system, DNS, is used very regularly. It's known as the phone book of the internet. Your computer has it whenever you go to a website, and it's a very long process, so I'm not going to explain the whole thing, but let's say you're requesting to go to a website in your browser that you've never visited before. So the DNS system is responsible for going, sending out a query saying, hey, what's the IP address that is associated with this name? And then once it collects that, it keeps it in its cache, in its host file. And so what happens after that is, instead of it loading slower every single time you try to go to that website, it loads it immediately quickly, or not immediately quickly, that sounds redundant. It loads it quicker. It loads it quicker because now it's in its internal hosts file, right? It's in its internal address book, you can say. So this is the essential part of web services. It's commonly used and trusted, and therefore often ignored. Due to that, adversaries use it in data exfiltration and C2 activities. So similar to the ICMP stuff, the anomalies appearing or starting after malware execution or exploitation, adversary creates or already has a domain address and configures it as a C2 channel. The malware or the commands that are executed after exploitation send DNS queries to that server. However, these queries are longer than the default DNS queries and crafted for subdomain addresses. These subdomain addresses are not actually addresses. They are encoded commands as shown below. So encodedcommands.maliciousdomain.com is typically what it looks like. And this portion right here is the very long element of it. So if we actually go to CyberChef real quick and do something like encoding. So if I do the base 64, so to base 64 is what I'm trying to do, right? So if I do that, now you can see this very short IP address is now turned into this very long thing. So if I do any kind of command right here, where we just are exporting files, right? We're exporting something out of our domain to somebody else's domain, out of our host into somebody else's domain. Whenever you do that, it actually sends the data. So I don't know, something like, touch file.txt, and then we'll do and echo etc hosts to file.txt, something like that, right? So let's say I create this file, and then I echo the contents of the host file into the file.txt. Let's say that's what I want to do. You see now this is this long command, right? It's encoded. So to the naked eye, you have no idea what that is. And then from there, they put that at the beginning of this portion. So they put that right here, and then you just have the domain.com. And that's how they get their commands across. When this is routed to the server sends the actual malicious commands to the host, and the DNS queries are a natural part of networking activity, so these packets have the chance of not being detected, as we already talked about. So you should know how to investigate this. So the global search would be DNS. Options for low-hanging fruit would be the length of the query, anomalous and non-regular names in DNS addresses, long DNS addresses with encoded subdomains, known patterns like DNSCAT and DNS2TCP, statistical analysis like the anomalous volume of DNS requests for a particular target, So not MDNS disables local link device queries. So that's something else to keep in mind. So if we look at this, right, DNS, which is the protocol, right, the global search here, contains DNS-CAT, right? Because we know that DNS-CAT is one of these specific protocols or tools that is used to export data. DNS.query.name.length is greater than 15 and not MDNS, right? So disable the local link, the local devices, and then look for a query name that is greater than 15. And so now you can look at all of these long subdomain addresses, right? These long DNS names to see if there's anything that we can find. So DNS contains DNS-CAT is the search here. And if we go right here, you can see DNS-CAT dot, and then there's some kind of encoded element that's connected to it. So that is a dead giveaway, right? So just knowing about something like DNS-CAT or DNS2TCP can help you with investigations like this, but then you can obviously use any of these other patterns, these other low-hanging fruits as well. So detecting these things in chunked files is easy, but we need to use our exercise files to actually do some proper investigation. So we will be using the DNS ICMP and ICMP tunnel PCAP for question 1, and then using the DNS PCAP for question 2. And there's just 2 questions. And so I am doing this in day 2. So I had to stop recording yesterday. So I had to launch our instance one more time. And it is here. So we will now go ahead and find the first question here, which says use the PCAP file, investigate the anomalous packets. Which protocol is used in ICMP tunneling? So the first thing we got to do is load the file, and there it is. I loaded it. So this is the ICMP tunnel PCAP file. And so they're asking for the protocol that would be used in ICMP tunneling, right? It says, so which protocol is used in ICMP tunneling? And we can go up here and kind of just look at it a little bit. So it would be data length greater than 64 and ICMP, I guess, and try to figure out which protocol it would be. That might be kind of like a good starting point. Packet length, ICMP destination address, encapsulated protocol signs in the ICMP payload. So let's see what we can find and what query we can use to find it. Okay, so I did the same exact query, okay? And after sifting and sorting through some of these, when we get to, I think it's number 39, yeah, like around number 39 is when we start seeing the payload change. So I'm gonna kind of zoom in here just so you can see what's going on. So this is the payload, right? This is the typically the payload that we can try to sift and sort through, and most of it a lot of times is jargon, but then you can start seeing things that are recognizable. For example, SSH 2.0 open SSH, right? And if we keep going, there's another one, and then it starts actually getting longer, and then you can actually see more commands, and again SSH SHA-1. So there's definitely it seems to be that there is definitely requests being made for the connection itself. And usually when you establish a connection via SSH, it actually gives you the SHA-1 key for that, or the SHA-1 encrypted hash for that connection. And then you just keep going in and you see the rest of the stuff. So the protocol for these ICMP packets, and then I'm just going to keep clicking through the rest of them just to see if there's anything else that stands out. But for sure, the protocol for that would be, for that tunnel, would be the encrypted protocol of Secure Shell. So, but if you ever wanted to kind of see what is inside of these things, with the exception of the actual packets themselves. So if we go up here, let me see if I can go back to those SSH ones, because I think I clicked too many times. So if once I find it, so here we go. So this is one of the SSH ones. So if we go over there and try to see the contents of it, you'll see that you won't really be able to, like the data right here, that's basically it. Like this is all that's available inside of the data. If I go ahead and copy the value of this data and take it to CyberChef, right? We paste that right there. You can see that over there. And so now we would want from base 64 and then get rid of the to base 64 one. So if I close that, you can kind of see that there's maybe potentially something here, but it's still not really reading. So it's probably not base 64 encoded. So that's not going to work. And let's see if there is any other version of this that we can look into that might potentially be useful for us. Because at the very least, I think that value could potentially be something that's useful for us. But unfortunately, I don't know what kind of encoding was used to decode it. So it's not really helping much. But if you can, if you get lucky or if you've seen this kind of encoding before, you might be able to see what potentially can happen. It actually doesn't look like base 64. I think it might be like maybe hexadecimal or something. But anyways, so if you can't notice it, right? If you can't figure it out, there we go. This seems a little bit more, yep, it is hexadecimal. So it's from hex is what we're trying to figure out. And then from here, you can actually see OpenSSH clearly, right? So this is the piece of it that we would need to go ahead and decrypt or decode to make sense of whatever the data is. So to take that piece and then to go over here and see the already decoded version of it, that's the hexadecimal decoded version of it, those are the ways that you can try to find some information. But that's basically what you would have to do, because for every single one of these, I would have to go and pull this data out of here, copy it, go to CyberChef, see if I can make any sense of it. So instead of doing that, I can just look at this little area and then see if there's anything already available for me that I can potentially kind of make sense of and decipher. So anyways, long story short of it, that is what we're looking for, and we're going to do SSH as the answer. For the next question, we're going to open up the DNS PCAP file, and then we're going to use that PCAP file to answer that question. And it says, investigate the anomalous packets. What is the suspicious main domain address that receives anomalous DNS queries? Enter the address in defanged format. So if I zoom out of this, look at the hint, it says, why does it go away so quickly? After filtering the packets, focus on the payload data in the packet byte section. You might need to use the tool. Same thing, I think, for this one, right? Filter anomalous packets, investigate packet decay. Security analyst should filter the packets, investigate it. Okay, fine. All right. Full screen mode, view full screen the VM. Look at the data bytes in the payload section is what they're telling us. Okay. So we are going to try to find that specific answer here, and let's see what we can come up with. Okay, so I mean, it makes it a little bit easier because I used the strategy that we did in the one of the previous questions. So literally on the very, very top right here, I just typed DNS. I didn't even do anything else. I just typed DNS, and then I went and opened the domain name system portion, went down to queries and opened these, and I right-clicked on this portion and I did apply as column, right? So I could actually see all of the domain names for every single one of these packets. And so at first glance, based on what we know, right, we can see that this one right here, and I haven't even scrolled down, this one right here is this super long kind of query that's in here. So if we scroll down, we can see there's other ones right there. And if we scroll down to the side, we can see that, okay, why is this happening like this? It was showing me a little bit. There we go. I'll just kind of drag the bar down here. So if we scroll down, we can see that, after that long portion, there's dataexfil.com. And then we come down here, and then it's also right here, dataexfil.com. And then if we just keep going, we'll see that it's dataexfil.com, dataexfil.com. So we see this, and they seem to be coming in sets of 2, and then they seem to be coming very consistently. So dataexfil.com, that's the only one that I can see that is even remotely relevant to what we're looking for. And so I will go ahead and defang that, and it feels like that would be the answer, because data exfiltration is like a really big hint just by itself is like data exfiltration. So dataexfil.com. And then so that's the defanged version. I could have probably just done this real quickly, just typing out those square brackets. But so there we go, dataexfil.com. And there's the answer. So it doesn't, for me, it didn't require much of a complicated filter. So I just added the DNS global portion, and then I made sure that I could see all of the domains in the columns so that I could actually look at the domains. And first glance, it was like the very first one. I was like, oh, look at this. There's like a super long subdomain that's attached to this thing. I wonder what's at the end of it. And then there's the hint, big hint, dataexfil.com. So I was like, okay, that's probably the answer to the question. So if I was a much better analyst, well, or you could argue that I'm a really good analyst, that I thought of doing it that quickly. But if I was better at creating filters and all those things, maybe I would go ahead and, find a bunch of stuff and do a bunch of different filtering things right here. DNS contains that, and the length name, or the length, and all of those things. But I didn't need to. So that's basically what we got. I think probably one of the ones that would have been like really handy for us to use would have been this one, the query name length greater than 15. I think that could have been really useful, because then it could have given us like all of the longer domains, and it would have gotten rid of most of the shorter domains. So that could have been kind of handy, and it would have given us these like super, super long ones. So let's just try that just for shits and giggles, you know what I mean? So query name length is greater than 15. Let me see what shows up here. Okay, so there you go. So that's also like a really good sign. But again, it's like you're kind of looking for these. So greater than 15 brings us the connectivity check Ubuntu and all these other guys. So maybe not greater than 15. What if we do greater than 20? See, there you go. That's a little bit better. So greater than 20 gives us very obvious data right here. So dataexfil.com, very obviously what it is that we're trying to look for. And then we can also do something like, if I do this and get rid of, so put that inside of parentheses, and then do and then do an exclamation where it says not, and then we can say, what is it? The name does not contain. So DNS contains, and then I'll do things like, let's say, I think the wildcard character should work. So in address.arpa. Let's get rid of that, right? So if I can also get rid of all the elements that include that in address ARPA, let's see, it doesn't look like it would be working. Oh, hold on, let me put this closing. There we go, closing. Well, it still showed it. It still shows all the in address ARPAs. So maybe not, maybe that's not the one, but close enough, you know what I mean? At the very least, we can kind of get some decent responses using the length version of it, which is one of the filters that they told us to use anyways. So anyways, that's our answer. We can now move on to the Cleartext protocol analysis. Okay, so Cleartext protocols come in various shapes and sizes. The one that we're going to be looking at is FTP in this particular section, but there are a lot of different Cleartext protocols. So for example, Telnet is another one. HTTP without the S at the end, that's another one. And I think that's actually one of the ones that we're probably going to look at. Yeah, HTTP is the next one. So when you're looking at these Cleartext protocols, the goal is really if any of these ports are even open, if any of these protocols are even open, it's actually a really, really handy resource for us to investigate, because everything is in actual clear text. It's not encrypted, so you don't have to decrypt it. So when you look at the requests and the responses and all that stuff, you're getting to see exactly the data that's being passed through without any encoding, any encryption or anything like that. So it actually can be very handy if the protocols are even open. So FTP is the file transfer protocol, and it's used for transferring files and sending commands back and forth, and the encrypted version of it is on port 22, which is secure shell. So that ends up being kind of like a really the updated version of everything. So for us, it's important to create statistics and results from the investigation process, and to be able to have the required network knowledge and tools and skills to accomplish this. So investigation for FTP would look something like this. We can probably find man-in-the-middle attacks. We can see credential stealing and unauthorized access. We can see phishing, malware planting, data exfiltration. All of those things can be done via the FTP protocol because it is the file transfer protocol. It can transfer files very easily, so it's more focused on simplicity instead of security, which is why it's Cleartext and nothing is encrypted. So if you just want to find the FTP stuff, you can just type in FTP and you'll see everything for it. There's a lot of different options that are going to be available here. So the X1X series for information request responses, X2X is for connection messages, X3X would be authentication messages. 200 as a response code means that the command was successful, so we'll be looking for things like that. There's no value inside of this, so it literally just says that you can look for these types of hanging fruit. This one for the X1X series, oh, there we go. I think they break it down like this. So they give us all the options. I don't know why they did this, but they could have just done it easily over here. But so the X1X series for low hanging fruit, 211, 212, and 213 are the status codes, right? So the response code 211 will give us a successful status code. So anything in the range of 200s means that it was successful. It's just that what type of request was being made and the data that was being requested, right? So in this case, 211 is the success code for the system status being retrieved. On the X2X series, 220 would end up being the service ready. 27 would be passive mode, long passive mode, extended passive mode. And so if we're looking for entering passive mode, we would look for 227. The X3X, and the way that they're saying it is that this is the first X, that's the second X. So we're looking for the 3 series, right? And that's basically kind of it right here. And this is the pattern that we're noticing. So for this, 230 is the user login, user log out. 331 would be valid username. 430 would be invalid username. 530 would be no login, invalid password. So in this particular case, our success messages are these. And then this one would say that you have a valid username, but I guess the password is invalid, or there was no password entered. 430 would be invalid username or password, and 530 would be no login. So if we got a 230, if we're searching for a 230, we're just searching for somebody who successfully logged in. And the commands themselves, the user, password, current working directory, and then listing things. These are common commands that would be used inside of the FTP connection once you've actually established your FTP connection. So if you type in user after you've connected it, you would be typing in your username after that. So you would type in user in all caps and then provide the username. You would type in pass and then provide the password. And then that's where the connection would be established. And then after you've connected, you can do current working directory to try to find something, right? So in the request commands, you can look for these. In the request arguments, you can look for password. And then advanced usage examples here. So brute force signal, listing the field or failed login attempts, listing target usernames, listing targets for a static password. So response code 530, and the argument contains username. Request command of pass and the argument contains password. These are just usage examples for potentially finding brute force attempts or password spray attempts. That could be the case. So if we look for FTP, as we can see right here, and we'll get all these responses here, all these packets. And if we look at the packet details, you can see the response code. So 530 login incorrect, not logged in, login incorrect, right? That's the one that they're on. But I mean, in the info section, you can also see it. That'll give us the response codes here. So if we wanted to, if you see a bunch of login incorrect taking place, and then if we were to look at the IP address that's requesting it, so 10.121.70.151 is the one that's trying to make these connections take place. and he's trying to connect to the same exact IP address at the end as well, but there's just a bunch of login incorrect that's being done. So that is an issue. And then finally, we get the response 220 FTP service. So that seems to be that they finally got the connection, and you can see that they're using, password Merlin, password Mercury, password Mets, and then finally password manager is actually available, or it's accepted, and they are connected. So this is a clear sign of somebody trying to brute force their way into the FTP server. So we're going to now use the information that we've learned to do an investigation of FTP. And so we have, how many? We have 4 questions on this, so it should be fun to do. Let's zoom out and go ahead and load our FTP PCAP file and begin our investigation. Okay, so here is the FTP investigation. There are 20,000 packets in here. So it says how many incorrect login attempts are there. So we know that if we want to do the incorrect login attempt, so we would be looking for something like invalid username or password, right? That would be an incorrect login attempt. So we can look for that, or we could look for the 530 response code as well, which is no login, invalid password. So we can do either of those, and really dealer's choice, as they say. So response code equals, which one was it? So we have 430 and we have 530. So let's try 430, and 430 gives us nothing. Okay, so let's try 530. Cool. Okay, so 530 we actually got something. And then we have 737, good Lord, 737 failed login attempts for that. So let's see if that is the right answer. That is the right answer, okay. Next one is, what is the size of the file accessed by the FTP account? So now what we need to do is we need to get a successful login, right? So that's the key piece. So after all the failed logins, we want to go find somebody, or the attempt that they finally got a successful login, which would be 230. So we'll go here and we'll switch it to 230 and get, okay, there's one successful login. Okay, so there we go. So now we need to just find the access, or the file that was accessed. So let's see. I want to say that what is the stream, or there was a way that we could actually go ahead and get the information from the actual interaction that this packet kind of marks. So it was conversation streamed. There we go, TCP stream, there it is. Okay, so if you just right click on the packet and then go follow TCP stream, it'll give you this stream of the requests that were made, right? So user FTP, password FTP, access granted, they got system, feature, etc., and then print working directory, entering extended passive mode, listing what's available here, and then so file list, and then type I, so type I, size resume.doc, okay, and let's see, extended passive mode, and now we're just trying to find the size of the packet, or the size of the file that was transferred. It has to be the resume.doc. So which one, what is the file, or the file size, I should say? Oh, you know what? Size resume.doc. There we go. So what is that? I think this, right? So that's it, because this is the response code. So that would be at 39424. That is what we're looking for. So let's see, 39424. Okay, great. So the way that we did this was we just looked for the successful login. And once we got the successful login, we went ahead, and so let me just do that one more time for you. So TCP response code, or I'm sorry, not TCP, excuse me, FTP response code, response, if I could just type to save my life, 230, FTP response code 230 for the successful login. It brings just one packet. That was a successful login. We right click on that, we do follow TCP stream, and then it brings up all the connections and the requests and responses and everything that was made from that. And then from there, we were just looking for a file. So clearly a file right here. And then the command itself is size. So just trying to find the size of that file, and there it is. So cool. Now, the adversary uploaded a document to the FTP server. What is the file name? Okay, so from our connection here, so if we try to make sense of the commands that are being made, print working directory, they're in the root directory, entering extended passive mode, opening ASCII mode, data connection for file list, type is set to I, and then the resume doc size, entering extended passive mode, opening binary data for resume collection, transfer complete, and then excuse me, current working, and then uploads is the current directory that they're in, entering extended passive mode, opening binary mode, transfer complete, test file exists, upload test directory successful created. So I want to say that resume permission denied, transfer complete. So they did, what is it? They transferred resume doc in here, I think. Because it says file exists too. So that make test directory, so make directory, test directory, and then I think, okay, so we'll try resume.doc. And then the next question is, what is the permission? Oh, right here, 777 is the permission to the resume.doc. So, okay, so first let's try resume.doc. Okay, that is the one. And then so now it says try to change the permission. What is the command used? It's chmod 777. There we go. So that one I recognize right away. And then the resume.doc is really the only one that is even a reference as far as a file is concerned. So that was kind of like, it was a guess, but at the same time, the making of the directory and then directory existing, I was like, okay, well, why are they doing that part? So that was the only way that I made the connection of the file that was being transferred to the FTP server, not necessarily being downloaded by the FTP server. The first one right here where it says, what's the size of the file accessed by the FTP account? That was kind of like misleading. So I thought that they were downloading it, but evidently they were not downloading it. They were uploading it. Okay, so cool. So now we can move on to the next one, which is going to be Cleartext Protocol HTTP. HTTP is the Cleartext version of HTTPS. There is, we have a pretty decent technical explanation for it here, but it's basically the protocol that is used to roam around on the internet. So usually when you do Nmap scanning, you'll see that HTTP port 80 will be open in conjunction with HTTPS port 443. And a lot of times, HTTPS will be open without HTTP being open because port 80 is, again, clear text, right? So you can actually see somebody entering their username and password if they're trying to log into a website, which is also one of the reasons why if you actually visit a website that does not have an SSL certificate or a TLS certificate and it's unencrypted, your browser will be like, danger, don't enter this website. Are you sure you want to enter this website, right? So the HTTP is the clear text request response and client server protocol. So your client, your computer, your phone connecting to a server, right? It's the standard type of network activity to request web pages, and by default, it's not blocked by any network perimeter. As a result of being unencrypted in the backbone of web traffic, it's one of the must-to-know protocols in traffic analysis. We can try to find phishing pages, web attacks, data exfiltration, command and control traffic, etc. So you can look for either HTTP or HTTP2, which is the revision of the original for better performance and security, but HTTP2 is also unencrypted, right? It's not encrypted. It supports binary data transfer and request response multiplexing. So the request methods would be get, post, and really there's put, there's delete, there's a lot of different HTTP requests that can be sent, but the most common are get to retrieve data and post to send data. So when you're sending your username and password, when you're entering your username and password, it's an HTTP post request, okay? Listing all the requests can help you. So if you do http.request, it'll list all the requests. But so request method post, request method get. Response status codes. So we talked about these already a little bit. 200 is that there was a successful get or post request, right? 301 is that moved permanently. So whatever you're trying to access has been moved permanently to a different path. Moved temporarily is moved to a different URL path temporarily. 400 bad request means that the server didn't understand the request that you made. So maybe you misspelled something. Unauthorized is that the URL needs authorization, for example, a login. 403 forbidden is that there is no access provided to that requested URL. 404 is that it wasn't found. 405 is that the method that you're using is not allowed or it's blocked. 408 is that there's a timeout request, so the server kind of just lagged out. 500 internal server error is that the request wasn't completed. There was an unexpected error on the server side. And service unavailable is that the server is down, right? Server or service is down. So this is basically a response code, and then you give it the response code that you're looking for. And that's how you can find the types of requests that are being made. Then we have the parameters. So the user agent parameter is typically a browser and the operating system that is using that web server or trying to access that server, right? So the browser and the operating system identification. The request URI is the requested resource from the server. So this will be like the URL specifically, the path to the image, let's say, or the path to the video that you're trying to access. The full URI is the complete URI information, which may include anything that was left out in the request. So when you request something, the actual response or the resource that's being accessed would probably sit on a completed URI, the Uniform Resource Identifier. So it will display in its response. So you request something from the server, and in the response, it'll say, okay, granted access to such and such, and it'll give you the full URI. And a lot of times it's just the longer version of what you requested. So looking for the user agent containing Nmap because somebody's trying to scan your web server, or requested URI containing admin because somebody's trying to access the admin login page. The full URI containing admin, same thing. The parameters for accessing things, so server, host, connection, line-based data, HTML form URL encoded. This is very good for trying to find login information. So if somebody's trying to actually access a login page and entering login information, that's what we would be looking for. So the server name, the host name of the server, connection status, Cleartext data provided by the actual server, and of course the web form. So HTTP server contains Apache server name. HTTP host contains whatever you think it might be. HTTP host equals whatever you think it might be. HTTP connection equals keep alive, right? That means that the connection should be still going, right? Or we're looking for something that instead of the connection being closed automatically because of some kind of error, the connection was keep alive. And so that means that the connection was established, or at least they did something correctly that they didn't get kicked out. The text lines, including the keyword, is something that you can also look for. And then there was the URL encoded something that we had to look for in an earlier task, that we can also look for that specific parameter as well. The analysis of the user agent is very important. So I'm just going to kind of skim through this a little bit. So the adversaries will use advanced techniques, right? Sophisticated techniques to try to leave traces that are similar to natural traffic. For us, it's important to spot the anomaly signs and bits and pieces of those packets. User agent is one of those resources for spotting anomalies. And adversaries successfully modify the user agent, which could look supernatural. A security analyst, and it doesn't say supernatural as one word, it's saying it as it looks really natural. That's basically what they're trying to say. So the security analyst can't rely only on the user agent. They never whitelist the user agent, even if it looks natural. The user agent anomaly and threat detection hunting is an additional data source to check, and it's useful when you know that there is an obvious anomaly. If you're unsure about it, you can always look through the web and try to find the default or some samples on it. So we have the database here. What is my browser for developers? And so we can look for user agents and all these things. This is actually another one of those great resources. I need to start organizing my resources right here, but I'm going to save this as well. And it's going to be what is my browser is what I'm going to save it as. And then ultimately I have to kind of start arranging these because I don't have any folders for them. But this is another really good source for trying to find that. So user agent analysis. The global search would be http.user_agent. And for a low-hanging fruit, so different user agent information from the same host in a short time. Non-standard and custom user agent. Subtle spelling differences. So Mozilla is not the same as Mozlila or Mozlila, like that, right? Audit tools like Nmap, Nikto, WFuzz, and SQLmap in the user agent field. This is a really big one because these things actually show up under the user agent field. And so if you're looking, if somebody's running Nikto against your server, or if they're running SQLmap against your server, it's very likely that they're trying to do malicious reconnaissance against you, right? And if the IP address that's running it is one of your internal IP addresses, okay, maybe it's not that big of a red flag, but they should not be running Nikto. They should be running Nmap. Nikto is like a web server kind of a reconnaissance, enumeration, brute forcing kind of a thing. It looks for vulnerabilities on a web page or a web server. So payload data in the user agent field is another one of those issues. So if we look for example, the HTTP user agent containing SQLmap, or HTTP user agent containing Nmap, or it contains WFuzz, or it contains Nikto, this is all one long query, right? You're trying to look for anything that might have any of these potentially in there, because all of these are signs that somebody's trying to do something that they shouldn't be doing. So we have right here, HTTP user agent is what's being searched. And so if we look at the user agent window, or the user agent column, I should say, so you have, Mozilla, Windows, okay, great. Mozilla, Nmap scripting, okay, that's not that good. And then WFuzz, and it's like, okay, well, that's definitely not good. But notice how the Nmap scripting engine actually shows up with Mozilla at the entrance of it. So Windows, NT, and all of that, that's great. But Nmap scripting engine being inside of that, that is definitely a red flag. And so, of course, WFuzz is also a big concern. So we can find that in the user agent field on packet details. Or if we were to look at the binary data, or not the binary, excuse me, the hexadecimal data, the granular details of it, we can also see it under the payload where the user agent was WFuzz. Then we have log4j, which is technically a campaign name. It was kind of like an attack that was done before that. Before, I guess, what is it? It says before launching WireShark. So I guess this is what we might be trying to investigate. That's kind of what it feels like. But this is a campaign that was previously done successfully. So if we're trying to investigate the log4j vulnerability, for example, so the attack starts with a post request, and there are known cleartext patterns like the JNDI LDAP and exploit.class. So these are key elements that we could look for. So we would look for HTTP request post, and IP contains JNDI or IP contains exploit. Frame contains JNDI or frame contains exploit. User agent contains $, because that would imply that it is maybe a host name, or user agent contains the double equals, which implies that it probably has a base 64 encoded, because base 64 encoding more often than not ends with the double $. And I'll just show you kind of what that looks like right here. So if we actually go to base, and then if we go to base 64, so we're converting it to base 64, and then that's the domain, right? But then the base 64 encoded is including the $2 at the end. So if we're looking for that, the hint, the idea is that we're trying to find something that is actually base 64 encoded. So in this case, this is what they search for. The user agent contains JNDI or user agent contains exploit. And then we see right here that right here, JNDI is contained in there. There's no one that says exploit, but JNDI was definitely in there. And then so we see that the very first one was the post request. And then if we go down to the details of that packet, and then we can see that the user agent has JNDI in it. So there we go, we found it. And if we go and look at the actual payload, we can also see JNDI in the payload as well. So these are clear signs, right, that somebody is trying to do the log4j, or they're trying to exploit the log4j vulnerability. So now we are going to use two PCAP files, the user agent PCAP and the HTTP PCAP, to answer these questions. The first two questions will be user agent, and then the questions 3 and 4 will end up being the HTTP. And that is it for this one. So let's go ahead and zoom out of this and go to our instance right here and open up the first HTTP PCAP file, which would be inside of this. So we're going to do, is it user agent first or HTTP first? It's user agent first. Okay, cool. All right. This has 54 packets in it. Okay, so not that bad. So the question says, investigate the user agents. What is the number of anomalous user agent types? So let's see if we can find anything that would be anomalous. We can probably like count them because there aren't that many packets, but let's see if we can find anything, you know, potentially anomalous. So in order to actually figure that out, we need to have a little column, right, that shows us the what is this name one? Can I delete this one? Can I remove this column? Remove this column. Okay, so now we have all of our columns here. So we're going to look for the user agent as a column. So I'm going to click on user agent, apply it as a column, and there we go. Now we have the user agent as a column. Kind of shrink it down a little bit just to be able to see the rest of our stuff over here as well. So we're looking for the, what is it? It says the anomalous user agent types. So let's see, we can find how many here. And let's see what the hint was real quick. Answer is not the number of packets, it's the number of anomalous user agent types. You need to filter the user agent as column and conduct a manual investigation of the packet details to spot the anomalies. In addition to the obvious non-standard modified user agent types, does Windows NT 6.4 exist? Okay. All right. So the answer is not the number of packets. It's the number of the types, right? So, okay. So we have a total of 54 packets. So Windows NT 6.4. Does Windows NT 6.4 exist? That's a good question. Windows NT 6.4 exist. Yes, Windows NT 6.4 existed, but only as an internal development of that, referred to as threshold. But while it was intended to follow, it decided to skip it for the final release to assign context. Early technical views identified themselves as 6.4. Okay, these builds were essentially intended to be follow-up. I mean, it says yes, but the phrasing of the hint is saying that it's not, or it's kind of implying that it doesn't exist, right? And technically, I guess it doesn't, because it was meant to replace something, or it was meant to be, but then something else replaced it. So there shouldn't be Windows NT 6.4 running at all, right? So if we say that that is malicious, right? So this is kind of a malicious thing. So Windows NT 6.4, that's one. And then we have Nmap, that's 2. WFuzz is 3. What else do we have here? SQL map is 4. Mozilla Linux, that seems to be fine. Google Chrome, okay. My Windows, Google Chrome, JNDI, there we go, that's 5. Apple WebKit Linux, Mozilla, Ubuntu Linux, Gecko. Okay, what is that, 5? Is that right? What's the answer? The malicious 5. It's not the answer. Okay. Ooh, there's one right here. It's Mozilla. So that would add another one to it. That's so tough to notice. Wow, man. Okay, so 6 would be the answer. Yes, okay. Wow, I totally missed that. Like at first glance, you don't notice it at all. but you really got to pay attention to it. Okay, so 6. What is the packet number with a subtle spelling difference of the use? That's the one right here. And so that would be packet number 52. Wow. Wow. Okay, cool. All right, so now we're going to go to the next PCAP, which is the HTTP PCAP file, which is this one right here. So it says locate the log4j attack starting phase. What is the packet number? And so to be able to find the starting phase, what did they do over here? They looked for this full query, right? The user agent contains JNDI and all of that. So we're looking for a request method of post because we know that that's the starting, right? So the attack starts with a post request. And then inside of the frame, I guess, we're going to be trying to find JNDI or exploit. So we're going to try to look for all of those things, right? So we'll do something along the lines of http.request method equals post and frame contains JNDI like that, right? Or frame like this contains exploit like that. So I guess I think I need to do this. I need to put this also inside of parentheses to make it right. And then exploit, oh, it's missing a quote. Okay, so all right, so let's see. Let's do this. Okay, I think that's it. That's a post, right? It's a post request. Yep. Okay, cool. So what is the question asking? Look at that. What is the packet number? I want to say it's packet 444. Nice. Okay, like the Jay-Z album. All right, so now locate the log4j attack starting phase and decode the base64 command. What is the IP address contacted by the adversary? And of course, in defanged format, and exclude the squiggly brackets. So we found the thing right here, and then we're looking for the base64 command. So the base64 command, you can actually see it right here. It's like this full thing. So if I can, can I copy the value? No. Okay, so let's go down here. Let's go to user agent. We're going to copy the value of the user agent down here. And we can go into CyberChef and we can kind of type the whole thing, right? So that's the whole thing. So I'm going to delete that. And then I'm going to delete the last squiggly, which will leave me with the base64. And then we're going to do from base64, right? So from base64, and then we're going to turn that off. And so there we go. So there's the IP address, okay? And there's the full command here. So we're going to take this IP address and we're going to copy that and we're going to paste it here. And now we need to go ahead and do a defang of IP address. And there we go. So that's the defanged version of the IP address. Fingers crossed. Let's see if this works. Excellent. Amazing. Okay, cool. So we got all of these guys. So now we're going to do the encrypted protocol analysis for decrypting HTTPS, because HTTPS is the encrypted version of HTTP. So as we already established that HTTPS is the encrypted version of HTTP, and so what we can do now is, or what we can assume with this case, is that there is no longer going to be anything in plain text anymore, and everything, all of the data inside of these specific packets are going to look like gibberish, right? Because it's all going to be encrypted. It can use SSL or TLS protocol to encrypt communications. So it's impossible to decrypt these things if you don't have the actual keys, right? So there's key pairs that are included. So because of this specific level, or because of this specific feature of it, this is actually one of the most secure versions of communication when it comes down to web traffic, which is why TLS certificates are used by Google and YouTube and Facebook and XAI and all of these different services, because it is the most secure way to do internet communication. So security analysts should know how to use key files, right, to decrypt encrypted traffic And really, like, you would be either provided key files or you would have to find ways to retrieve those key files. Otherwise, without those key files, you won't be able to decrypt and analyze HTTPS traffic. So protocol info fails, like the addresses and all these things from the server, will not be visible. The first image will show them encrypted with the TLS protocol, and then we'll see if we can also decrypt it using our key pairs. So the parameters themselves, right? So the request, TLS, the client request, server response, local, simple service directory protocol, or simple service discovery protocol. And so we have the HTTP request, TLS handshake type 1 and 2, and then SSDP. SSDP is the network protocol that provides advertisement and discovery of network services. So we can see right here. So if we go over here, and you can see TCP, right? And that's the port trying to connect to port 443, which is the encrypted port, right? And then we have a TLS response that it says, hello, client, etc. And then we try to connect to it, and then, or excuse me, there's the client hello. So it's the same thing. So it's actually, both of these are coming from the same IP. So the first two are from the requesting IP, and then the second two are from the responding, right? I think, because yes, client hello, and these first two lines are from us requesting, and then the second one is it's responding to us, and then we have that. Once the connection has been established, we can see this cipher change. There it goes. That makes sense. Okay, that makes much more sense. So this basically is just the handshake. I'm so sorry for like the confusion of that. I was thinking out loud. But basically what's happening is that this is the handshake of us connecting to the TLS encrypted server. And then finally, at the very end, the server replies and says hello, and we're changing the cipher because now it's going to encrypt the communication. So that's what we got. So my apologies for not being able to kind of understand that. But so this is the one right here. So it says the HTTP packets encrypted with the TLS protocol. That's what we're looking at right here. So similar to the three-way handshake, the TLS protocol has its handshake. The first two steps contain client hello, server hello, and then the filter shows the initial hello packets with the capture file, and they're helpful to show which client address are involved. So client hello, this is what we're looking for, and then server hello, this is what we're looking for. So TLS handshake type 1 is the client hello, and then type 2 would be the server hello. And so we can see that right here. And we're going to do not SSDP right there, because again, SSDP is a network protocol that provides advertisement and discovery of services. So we don't want that. We want everything that does not include that specific protocol. So then we get it, right? So now we get to see that the request or TLS handshake type equals 1. So this is the actual request itself. So all the client hellos to Google APIs and safe browsing, client services, Google Ads, DoubleClick, Gstatic, all these things, right? And then so if we go into it, we can also see the details, and then we can also see inside of the payload the data that would be relevant, right? So there's that. And then so if we do the server hello, which is the type 2, the handshake type 2, we'll get all of these server hello responses. And then inside of that, you'll see change cipher spec, right? So these are the ones that are saying that everything is now going to be encrypted, right? So everything is now going to, from this moment on, the server is going to encrypt all the communications. And then you won't see much after that. As far as Cleartext is concerned, you won't be able to see anything. So now the encryption key log file is the text file that contains unique key pairs to decrypt encrypted traffic. These key pairs are automatically created per session when a connection is established, and these are processes that are all accomplished in the browser. So you need to figure out your system that uses a suitable browser, for example, Chrome and Firefox, to save these values as inside of a key log file. So to do this, you'll need to set up an environment variable and create the SSL key log file. And the browser will dump the keys to this file as you browse the web. So this is something that you can do on your own computer or your work computer if you're trying to get this kind of data, right? The SSL TLS key pairs are created per session at the connection time So it's important to dump the keys during the traffic capture. Otherwise, it's not possible to create or generate a suitable key log file to decrypt that. So it's very unique to a session. So just keep that in mind, right? These key log files or key pairs are very unique to each individual session. You can right-click menu, edit preferences, protocols, TLS to add or remove key log files. And so once you do that, you should be able to actually see the data. So in this particular case, let's see what this says. So it says adding key log files with the right-click menu. I don't know. I don't see anything here. So adding it with edit preferences, or maybe this is supposed to be, I think this is like one of those animated GIFs. So let's see if we can see. Yeah, it is an animated GIF. So they click on the packet, then they click on transport layer security, and then they'll do protocol preferences, master key log file name, and then the key log file name path, I guess. This is where we would put, right? And is that it? I think that's it. So that's what that is. And so this was the version where we do the right click menu. And then this is the version where we do edit preferences, protocols, and TLS. So if we look at this image now, they go to edit, they will go to preferences, they will go to protocols, and then they will go to TLS. So let's go ahead and watch them do this. I'm talking much faster than the person's actually doing it. And they're scrolling. This is insane. There are so many protocols. That's pretty crazy. So he got to T finally. Okay, go ahead and click TLS, bro, for the love of God. There we go. Okay, great. And then the debug file is what we're looking for. And then I guess we would put the debug file in there. We would browse and put the file in there. That was way too long. Viewing the traffic with or without the keylog file. So this is what it looks like, I guess, without the keylog file. And then so now they're going to go ahead and do protocol preferences, and they will do master keylog file name. And then they will go ahead and enter or browse the keylog file. So keylog file txt, there we go. Open it, and let's see. Click OK, and it should show us the, there we go. So there's the decrypted version of it, which we'll be able to see the hypertransfer protocol. If we clicks on that, he'll be able to see the data. And I guess there it is. Okay, cool. All right, so fair enough, easy enough. Traffic details are visible after using keylog file. Note that the packet details by bytes pane provides the data in different formats. Decompressed header of the info and the HTTP packet details are available for decrypting. Depending on the packet details, you can also have the following data formats: frame, decrypted TLS, header, etc., etc. So detecting suspicious activities is in our exercise PCAP file for HTTPS. And we have 1, 2, 3, 4 questions for this. So let's go ahead and load the file. Excuse me. And let's go ahead and have some fun here. So let me make sure that our virtual machine is still good and up and running. And you know what, while we're here, let's just go ahead and add some time to our virtual machine so it doesn't just die out on me. Okay, great. So we are going to now open the HTTPS file. There we go. There's the keylog file, so it's already there. So we're going to open up the PCAP, and right here, so we need to decrypt it with the keylog, right? So that's basically what it says right here. So let's see. It says, what is the name of the client hello message sent to accounts.google, or what is the frame number of the client hello message sent to accounts.google.com. So that one we can actually find, I think, without decrypting it. So let's go ahead and find that specific frame. So let's see. So we're looking for the http.request and, right, or excuse me, or, and then it says the TLS handshake type equals 1. So that's what we're looking for the client hello. And then we're gonna say also not SSDP, like that, and let's see what we get. So here's what we got. So user agent, I'm going to remove the user agent column. So client hello, and we're looking for the one sent to Google, but I guess I would have to do the the key first? Because that, it should show it, right? It should show me the actual communication that I would have with Google. So for whatever reason, handshake hello and the cipher, etc. Let's see. Yeah, it's not actually showing me. So I'm going to just do the keylog file right now just to see what is going on with this. So we're going to go to preferences. We're going to go to protocols, and inside of protocols, we're looking for TLS. So we're just going to go all the way down to T real quick. And then from here, we're going to do TLS. Then we're going to browse, and we're going to attach our keylog file, which is going to be inside of HTTPS. And there's the file. Save it. Already exists. You want to replace it. Oh, really? So it's already there? So why isn't it loading everything for me? That's annoying. Okay, so maybe there's something that I'm missing that I can't see the actual domain, because you can see it right here, right? Like, I'm not losing my mind. You could see under info, we can see client hello. So I should also be able to see client hello. So maybe there's some kind of an issue with the actual data itself. So let me see if there's a column that I'm missing or something. Okay, perfect. So there we go. So it's actually not the way that I thought it was going to be named. So it's under the handshake protocol portion, and we go down to the server name and then server name indication. So once we expand these, we can see now server name is right here, client services.google APIs. And then I just added that. I right clicked on it and I added it as a column. And so now we actually have the server name. So we're looking for specifically the client hello that goes to accounts.google.com. And so there is accounts.google.com, and it is number 16. So it's packet number 16. Okay, so very good. So it says decrypt the traffic with the keylog file. What is the number of HTTP2 packets? And the hint, let's see what the hint says. Import the key file to decrypt the traffic. I already did that. So we're looking for HTTP2 packets, and there was a filter up here that kind of showed us the type of HTTP2, right? Or no, actually, I think it was in this one for HTTP2 right here. So let's see if we just type in HTTP2, if it'll just kind of work just like that for us. Okay, so it's definitely not that. So let me see. I think there needs to be like a specific filter that I'm going to create to find the HTTP2 packets. Okay, so I crashed the machine, I restarted the machine, I restarted WireShark, and essentially I went on transport layer security, right clicked on it, protocol preferences, master keylog file name, and then down here is where I put the keylog file name. This one up here I didn't change, I put it down here. And then clicked OK, and then everything worked. And then right here, I went and just typed HTTP2, and it actually brought up the HTTP2 packets. So that the filter itself, the display filter, is HTTP2. It's just for whatever reason, it wasn't actually loading. And so I had to restart everything. So 115 is the number of packets that we have here. Now it says go to frame 322. What is the authority header of the HTTP2 packet? Enter it in defanged format. So we're going to go to frame 322 right here, right? 322 or 332? 322. Okay, so now we want to go look for the header in this location here. Header for the authority. So if we go down here, we have the authority header, and it says safe browsing. So we're just going to right click, and we're going to copy the value of that. Go to CyberChef, enter it here, and we're going to do defang URL. And so there is that. So we're just going to copy that and come back to our question here. And there is that. So investigate the decrypted packets and find the flag. What is the flag? So what's the hint? It says you can export objects after decrypting the traffic. Okay, so we can go to File, Export Objects, and we're going to export HTTP objects. And we have a couple here. There's the favicon, and then there's this one right here that has this like really long name. That is a very long name for a file. So I'm guessing that's the file. It can't be the favicon. Well, we're going to save it, and we'll save it to the HTTPS folder just to be consistent, you know. Okay, so we saved the file. So we're going to minimize this, and there's the file. So let's see if we can open this. And there we go. So the flag is THM packet master. So we're going to copy that bad boy or bad girl, whatever. And there we go. So there is the flag. So now let's go look at the bonus here. The first bonus is to hunt Cleartext credentials. So as mentioned, WireShark is not an IDS, but there are some use cases for expert info. Sometimes anomalies replicate, detention becomes harder. So for example, Cleartext credential hunting is not easy to spot multiple credential inputs and decide if it's a brute force or just a standard user who forgot their password. Everything is presented at the packet level and it's hard to spot multiple username password entries. The detection time will decrease when an analyst can view credential entries as a list. And so WireShark has a feature to help us do this. Some WireShark dissectors would be FTP, HTTP, IMAP, POP, SMTP. They're programmed to extract Cleartext passwords from the capture file. You can view these using the Tools Credentials menu. It works only after specific versions of WireShark. And since the feature works only with particular protocols, it's suggested to have manual checks and not entirely rely on this feature to decide if there's a Cleartext credential. Once you use the feature, it will open a new window and provide detected credentials. Shows the packet number, protocol, username, additional information. It's clickable. Clicking on the packet number will select the packet containing the password, and clicking on the username will select the packet containing the username. So that's what it looks like. Tools Credentials gives us a list, and then username admin. And then that's pretty cool. I mean, it's really handy. So it says use the desktop exercise bonus exercise PCAP file. What is the packet with the credential using HTTP basic auth, and then the packet number where the empty password was submitted. So, whoops, we need to zoom back out again. Go over here. We can close this guy out now. Go to exercise PCAPs. Let me also just close this just so the machine doesn't lose itself, really. Bonus exercise PCAP. Okay. Let's see here. Let's see what we can find. So the question again is packet number of the credential using HTTP basic auth. And the hint says tools credentials. Okay, fine. So we're looking for HTTP basic auth. So we're going to go to tools, credentials. And there we go. Protocol right there. HTTP basic auth is right there. And then AFIISKC. So packet number actually is 237. So 237 is that one. And what is the packet number where the entry password with the empty password was submitted? So we can go find the usernames, and I'm gonna just go to this one for now just to see if there was an empty password submitted here. Let's see if we can actually find that. So get method is get. We need to find a post method actually. So that's the key element. We need to find post method. How many do we have? So we have 243. So if I do HTTP request method equals post, because that would imply, and there is no post method. Okay, so never mind. Because I was gonna say that would imply that they sent the password, but the one username and pass and things like that, those are the key things that usually are sent via a post request. But for whatever reason, I think maybe that was the issue, is that the protocol was the HTTP, so the maybe FTP protocols don't have the post request. So okay, so we'll just look at it, and so all of them actually have this right down here nicely. So let's see, argument moose, so that one has a password, that has a password. I'm gonna click through all of these to see which one has a empty password. Okay, it's packet 170 that does not have a password so far, and the rest of them have passwords. So packet 170 does not have a password. Very good. All right, so now we're going to go to our next bonus here. Actionable results is the name of this one, and specifically we're going to be talking about creating firewall rules. So WireShark is not all about packet details. It can actually help us create firewall rules, and we can go tools, firewall ACL rules menu, and once you choose this, it'll open a new window, provide combination of rules for different purposes. These are generated for implementation on an outside firewall interface. It can create rules for net filter, Cisco, IP filter, IP firewall, packet filter, and Windows firewall. Very cool. So we would go tools, firewall rules, and then boom, we have a bunch of stuff. And then we can do create rules for a specific thing. So IP tables, for example, is the net filter, which is typically on Linux. And so inbound deny, for example, could be the rule, IPv4 source address. So it's actually really handy. This is actually very, very cool. So we're going to use the same PCAP file, select the packet number 99, create a rule for IP firewall. What is the rule for denying source IPv4 address? So let's zoom back out here. So same thing, so we don't need to change our stuff right here. So we're going to do firewall ACL rules, and we need to actually, so okay, let me go to what it says, packet 99. So we're going to go to packet 99 first real quick. And then for packet 99, so we'll click on that one, tools, firewall ACL rules, and it needs to be for the IP firewall. So we're going to go down here, we're going to click IP firewall, and we want to do what? Denying source IPv4 address. So IPv4 source address right here. Can I click on it? What's going on? It's not letting me click on anything. I feel like I should be able to click on stuff. So it's add deny IP. I'm going to type it out in a different window real quick, just so I can copy paste it. So it says add deny IP from IPv4. Yeah, so 10, 121.70, and 151 to any in. I believe that is the rule. So we're going to copy that now, paste that. There you go. Okay, so that's what it is. I guess it's not something that I can copy. So select packet number 231, IP firewall rule. What is the rule for allowing destination MAC address? So we're gonna, I could have, well, I can't copy anything because I can't, oh, there we go. That's what it is, maybe. Okay, close. So we're going to packet 231, and on packet 231, we're gonna go to tools, firewall rules. We're gonna do the IP firewall, allowing destination MAC address. So change this to IP firewall, and we're looking for allowing destination MAC address. Let's see where that is. MAC address source, and we want source address allow. Where is it? Why can't I find inbound deny? So let me take that and take off inbound as well. So I'm going to take off deny and take off inbound. So now we're looking for things to be allowed, right? So destination MAC address, add allow MAC, there we go, to any out. I got to be able to copy this because I'm not going to type that out, man. That's insane. So we're going to copy that. Let's see if that actually copied. It did not copy, or did it? Hold on. It did. Okay, wonderful. All right, so there we go. So now we can go here and paste that here. Wonderful. Sounds amazing. We are officially done, my dear friend. This was cool. This was a long one. It took me a couple of days and let's say like 4 hours in total to record this thing, because there were some challenges, and then I had to re-record a specific section because my freaking OBS stopped recording. I was losing my mind when I found that out. Thankfully, I didn't go through the whole thing and then realize that I wasn't recording, and because I would really go insane. It's like very disheartening when something like that happens. Okay, so we covered WireShark, and we went into some pretty advanced stuff and really handy stuff. There are now WireShark challenge rooms like Carnage, Warzones 1 and 2, and it's really handy to know this tool. This is like the industry standard tool when it comes down to granular packet analysis. Again, it's not an IDS, right? It's not something that is going to detect things for us. But if you know what you're looking for, this is a very, very good tool to help you do some deep dives into stuff. These would also be other rooms that we can use. For example, Network Miner, Snort, Zeek. And I think all of these are in the SOC Level 1 pathway that we're on. So I think we're probably going to retouch on these again, because I've already done all of these rooms probably over a year ago, but ever since then there have been updates to the data and the information, as well as just my skill set. So I think I can probably teach better when it comes down to these specific rooms. So we'll be covering those again, and I'm just very excited to go through the rest of it. And this was one of the rooms that, like, when I saw the length of the room, and each one of these things is like super in depth and it's like a really long lecture portion, I was like, okay, well, this is kind of intimidating, but we got it done. So at the very least, we got it done. And if you've made it to the end, and if you're here now, then drop a comment saying that you made it to the end and you watched everything, just so I can give you some kudos and some recognition in the comment section. But I hope you actually got some value out of it, and you actually learned, and you were able to find the answers, and you learned how to find the answers. More than getting the answer, I hope you actually learned how to find the answer. All right, that's it. If you found value in this video, and if you'd like to get more videos like this one, then I encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel, especially as we dig deeper into SOC Level 1, as we go and wrap up the CompTIA Pentest Plus labs, as we go ahead and get further into AI for cybersecurity and API integration. And then there's going to be CompTIA Linux Plus, the new 2026 version that's going to come out. There's a lot of stuff. Every time I do a video, I add more videos to my pipeline of videos that I'm supposed to create. So it's not going to stop anytime soon, and there's going to be a lot of other stuff that's going to come out. So if you have not done so already, make sure that you drop that subscribe. And if you have any questions about what we talked about today, or comments or anything like that, please drop it in the comment section below, just so I can get to your question and help you kind of work through any challenges you might be having. And that's pretty much it. There's a bunch of content that's available on our channel. There's a bunch of playlists, there's courses, a bunch of great stuff. And I'm working on becoming accredited with CompTIA so that I can get you discounts on your exam vouchers, which will end up being another massive benefit that I think will save our students money and help you get your certifications faster and easier, if that's something that you are really interested in doing. So if you have not done so already, make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. If you want access to my notes and exclusive downloads, and to get lifetime access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers. We have the supporter, the agent, the guardian, and the master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every single month, plus so much more. And to join, you can simply click the link in the description below, and you will be able to choose the tier for which you want to join. I really hope I see you in the Discord chats. If not, I hope I see you in the comment section. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker / protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease. And I'll see you in the next video later.